Hello there, and welcome to Life Beyond Seen, where curiosity drifts a little slower and science takes a gentler route into the unknown. Tonight we're heading somewhere almost everyone has imagined but very few will ever visit, a place both familiar and yet profoundly alien. You see, the Earth is wrapped in oceans so vast they cover more than 70% of the planet, and yet the truth is that most of that watery world remains hidden from us. We've mapped galaxies with telescopes, sent spacecraft past Pluto, and peered at light from stars billions of years away. But when it comes to what lies beneath the surface of our own seas, we've barely skimmed the surface. The deep sea, that immense and shadowed wilderness, is still mostly a mystery. Think about that for a moment. You could take a globe, run your hand across the oceans, and realise that almost all of it is unexplored territory. The mountains beneath the waves are taller than the Himalayas, the trenches deeper than anything on land, and yet what lies there is known only in fragments. It's not because no one is curious. On the contrary, the sea has pulled at our imagination for as long as humans have been telling stories. It's because getting there, surviving there, and seeing what really happens in that eternal darkness is one of the hardest challenges science has ever faced. Before we drift further into this ocean of questions, let me ask you something simple. Where in the world are you listening from tonight? And how close are you to the sea right now? Are you inland, far from the coast? Or do you hear waves not too far away? Some of you might be in places where the nearest ocean is hundreds of miles from your door, and some of you might smell salt air if you open a window. It's a curious thing that no matter where we live, the ocean touches us in ways we don't always think about, from the weather above us to the air we breathe. So while you're listening, think of your own relationship with the sea. Have you stood on a beach and stared out across the horizon, wondering what lies below that endless blue? And while you're here with me, if this quiet journey into science helps you relax or gives you a moment of calm after a long day, I'd be grateful if you gave the video a like, maybe subscribed, maybe even shared it with someone else who might enjoy a little late-night curiosity. It helps this calm corner of the internet reach other people who might need it. But whether you do or not, I'm glad you're here. So settle in, slow your breathing, and let's begin exploring why most of the deep sea is still a mystery. When you think of the sea, perhaps you picture sunlight sparkling on the surface, seagulls calling, or ships moving slowly along the horizon. But the surface is only the faintest introduction. Beneath that thin, bright layer, the world changes quickly. Sunlight only reaches down about 200 meters, maybe a little more, but then it fades into twilight, and soon after, into complete darkness. That's where the real mystery begins. It's not that no one wants to go there, it's that doing so is almost unimaginably difficult. The deep sea starts a few hundred meters below the surface and extends down to more than 11 kilometers in places like the Mariana Trench. Imagine stacking Mount Everest inside the ocean and still having water above its peak. That's the kind of depth we're talking about. Now, here's the strange part. Despite the difficulty, despite the extreme conditions, the ocean floor is not empty. It's full of mountain ranges, valleys, plains, canyons, and trenches. It's a landscape as varied and dramatic as anything on land, but we know far less about it. Less than 25% of the seafloor has been mapped in any detail. Some estimates are closer to 5% if we're talking about high-resolution surveys. That means that more than 3/4 of Earth's surface is essentially blank space to us, a mystery we've yet to fill in. Why does that matter? Because down there is not just empty rock. Life thrives in places we once thought impossible. Entire ecosystems exist without sunlight, powered by chemical reactions at hydrothermal vents. Creatures we'd once have thought belonged only in myths glide through the blackness, glowing with their own bioluminescent light. The deep sea is not barren, it's full of secrets waiting to be discovered. But those secrets don't reveal themselves easily. They're guarded by crushing pressure, near freezing temperatures, and darkness so complete that ordinary cameras and eyes are useless, and so we arrive at the central mystery. Why, in a world where we can track satellites, unlock genomes and build machines that touch the edge of space, have we still not unlocked the mysteries of our own oceans? Why does most of the deep sea remain beyond our reach? That's what we'll explore together. The reasons stretch across physics, biology, technology, money, and even psychology. It's not just about water, it's about the limits of what humans can build, the risks we're willing to take, and the strange pull of fear and fascination the ocean has always held over us. The deep sea has always been more than just a place. It's been a backdrop for human imagination, from sea monsters drawn on ancient maps to tales of lost cities. But the truth might be stranger than all of that, because the reality is still hidden. We don't know what's living in the deepest trenches. We don't fully understand how life survives without sunlight. We don't even know the full shape of the seafloor beneath us, and that is remarkable, because in so many other parts of science, we pride ourselves on what we know. Yet here, on our own planet, mystery still rules. So as we continue, keep this in mind. You and I are about to explore a frontier that's been here all along, one that begins just beneath the waves. We'll drift through the challenges of pressure, darkness, and cold. We'll look at the limits of our machines, the dangers of cost and distance, and the surprises of strange ecosystems. We'll ask why space exploration often takes the spotlight while the ocean stays in shadow. And along the way, we'll uncover just how much is left to learn about the deep. The deep sea is not an empty void. It's a place teeming with mystery, one that still resists even our best efforts to understand it. And that resistance is why it remains so captivating. For now, let's take our first step and begin with the ocean as an unknown world. When you think of the ocean, maybe you picture it as something we already know. After all, people have been sailing across its surface for thousands of years. We cross it in airplanes daily, we vacation at beaches, we fish in its waters, and satellites take pictures of it from space. It feels familiar, like something we already understand. But the reality is that this surface-level familiarity is deceptive. The ocean is not one single place. It's an entire world, layered and diverse, and most of those layers are almost completely hidden from us. It's not an exaggeration to say that the ocean is as mysterious as another planet, and in many ways, it truly is. On land, we see mountains, forests, deserts, rivers and plains. We know where most of them are, we've mapped them, and we understand how they formed. Beneath the waves, there's an equally rich variety of landscapes, but most of them remain unseen. Picture vast mountain ranges that dwarf the Rockies, canyons deeper than the Grand Canyon, plateaus the size of continents, and trenches so deep that if you dropped Mount Everest into them, its peak would still be underwater. This geography doesn't just exist in fragments. It stretches across the entire sea floor, and most of it has never been explored in detail. It's tempting to assume that because satellites orbit Earth and send us endless streams of data, we must already have a complete picture of the ocean. Satellites do help. They can detect subtle variations in sea surface height, which in turn reveal the presence of large undersea features. But these measurements are rough, averaged over kilometers. They give us a blurry outline, not a detailed map. It's like looking at a mountain range through fog. You know something is there, but the peaks, the valleys, the cliffs, the ridges, all remain fuzzy. Only direct measurements from ships using sonar can give us sharp images of the seafloor, and those surveys take time, money, and patience. The result is that while space telescopes let us see the surface of Mars in crisp resolution, huge portions of our own planet's ocean floor are blank spaces on the map. And that blankness isn't just about geography, it's about life. We know that Earth's biosphere is dominated by the ocean. Most of the living space on this planet is underwater, and most of that is deep sea. Yet what's down there is still almost completely unknown. Scientists occasionally bring back new species from the depths, creatures that look like science fiction inventing itself. fish with transparent heads, shrimp that carry glowing bacteria, worms that thrive in boiling water near hydrothermal vents, jelly-like animals that defy easy classification. Every time we look more closely, we find something we didn't know existed. That's the definition of an unknown world. The irony is that people have always suspected the ocean hides strange things. Ancient sailors told stories of monsters, whirlpools, and mysterious lights. Maps from centuries ago included drawings of sea serpents and colossal squids. These were exaggerations, of course, but they came from somewhere. Sailors glimpsed real creatures, real movements in the water, and their minds filled in the gaps with myths. And in a way, not much has changed. Even with our technology, the ocean still forces us to fill in gaps with imagination. Only now the myths have shifted. Instead of dragons and serpents, we talk about undiscovered giant squids, alien-like fish, or even potential unknown ecosystems that could change our understanding of life itself. If we think of the ocean as a separate world, it's not just because of what it hides, it's because the conditions there are so different from the surface. On land, we depend on sunlight. Plants grow, animals eat plants, and ecosystems build themselves from that starting point. In the deep sea, sunlight doesn't reach, and life has had to invent entirely different strategies. Chemosynthesis, where microbes use chemicals from the earth itself to make food, replaces photosynthesis. Bioluminescence takes the place of daylight. Pressure reshapes physiology. Creatures evolve in forms that wouldn't make sense anywhere else. These aren't just unusual adaptations, they're ways of existing that feel as though they belong on another planet. That's why many scientists say if you want to understand what alien life might look like, you don't need to go to Mars, you just need to look into the deep ocean. What makes this idea of the ocean as an unknown world even more striking is how close it is. You don't need to travel light years to reach it. You don't even need to leave Earth's surface. The frontier begins just below the waves, and yet it remains stubbornly out of reach. That closeness, paired with its inaccessibility, makes it uniquely frustrating. We live on a planet where the majority of habitable space is in the ocean, and yet we interact with only the smallest fraction of it. The idea that our homeworld contains vast, unexplored realms is a reminder of both the limits of human exploration and the scale of what still waits to be discovered. The unknown quality of the ocean also explains why so much art, literature and film has turned to it as a source of inspiration. The ocean is the ultimate setting for mystery. Think of stories like 20,000 Leagues Under the Sea, or films that imagine monsters rising from the depths. They tap into the same feeling. Here is a world that belongs to us, and yet does not. Here is a world that we depend on, and yet barely comprehend. And because we barely comprehend it, we fill it with fear, wonder, and possibility. But it's not just culture that makes the ocean mysterious. It's the hard limits of physics. Water blocks light. Water absorbs radio waves. Water distorts signals. In space, we can send a radio signal across billions of kilometers and still pick it up. In the ocean, a few hundred meters of water cuts us off. That's why submarines rely on sonar and why remote communication in the deep sea is so hard. The ocean is opaque in ways space is not, and that opacity keeps its secrets safe. When you put all of this together, the picture is clear. The ocean is not just unexplored, it is actively resistant to being known. Its scale, its conditions, its physical properties all make it a world apart. That's why when scientists talk about the deep sea, they often describe it as Earth's final frontier. It's the last great unknown left on the surface of our planet, and it's vast enough that even with modern technology we've only scratched the surface. And so, when we say the ocean is an unknown world, we're not exaggerating. It's a statement of fact. Most of it is unmapped. Most of it is unstudied. Most of its species are undescribed. And yet it's not just about what we don't know. It's about what we will eventually know. Because every expedition, every dive, every new piece of technology brings back glimpses of that hidden world. And those glimpses are enough to remind us that we've only just begun. If you've ever stood at the edge of the sea and felt the pull of the horizon, you've felt a fraction of that mystery. The horizon is not just distance, it's the threshold of a world beneath, and that world, for now, remains unknown. Which brings us to the next question. If this world is so vast, so close, and so obviously important, why have we explored so little of it? For all the fascination and importance the ocean holds, it remains astonishing to realise just how little of it has been explored. Scientists estimate that less than 5% of the deep sea has been directly studied in any meaningful detail. That number is not a rough exaggeration meant to spark curiosity. It's a stark reality. More than 95% of the deep ocean remains essentially untouched, unknown, and unobserved. If you imagine drawing a map of your own house and labelling only a single room while leaving the rest blank, you'd have a sense of how incomplete our knowledge of the deep ocean truly is. So the natural question is, why? Why, in a world full of satellites, advanced robotics, powerful computers, and human curiosity, have we explored so little of a place that makes up the majority of our planet? The answer is layered, stretching across physics, technology, economics, and even psychology. The most obvious reason is physical limitation. The ocean is deep, and depth brings with it extreme pressure. At the surface, the weight of the atmosphere presses down on us at about 1 atmosphere of pressure, a force we don't notice because our bodies are adapted to it. But descend into the sea, and for every 10 metres, another atmosphere of pressure is added. At 100 metres, you're under 10 times the pressure at the surface. At 1,000 metres, it's 100 times. At the bottom of the Mariana Trench, more than 11 kilometres down, the pressure is over 1,000 times what you feel on land. That's the equivalent of several elephants standing on every square inch of your body. For machines, it's just as punishing. Metal bends, seals break, electronics fail. Building something that can survive those pressures is not impossible, but it's expensive, slow, and requires constant innovation. And every time you want to go deeper, the engineering challenges multiply. That leads to the second limitation, technology. Submarines and remotely operated vehicles, or ROVs, are among the most advanced machines humans have built. They can withstand crushing depths, carry cameras and sensors, and bring back samples from places no diver could ever reach. But they're limited. They move slowly. They can only cover small areas at a time. Deploying one takes a full research ship, a trained crew, and often weeks of planning. And even then, the vehicle can only operate for a limited duration before needing to return to the surface. Autonomous underwater vehicles, or AUVs, can roam without direct human control, but they too are limited by battery life, communication barriers, and the need for careful retrieval. Compared to satellites orbiting in space, which can scan entire planets in hours, deep-sea exploration is painstaking, localized, and difficult. Communication adds another barrier. In space, we can send radio signals across millions of kilometers and still receive them. In the ocean, water blocks radio waves almost immediately. Signals don't travel well, which means most underwater vehicles must be tethered with long cables to maintain a link with the surface. Those cables restrict movement and add complexity to every dive. Untethered vehicles must rely on acoustic communication, which is slow and limited in bandwidth, or operate silently and record data to be collected later. It's a bit like exploring with one hand tied behind your back, unable to talk clearly to the surface, hoping that the machine does its job before its power runs out. Even if the technology exists, cost quickly becomes the next obstacle. Ocean research is expensive. A single expedition can cost millions of dollars, requiring specialized ships, trained crews, and equipment that must survive punishing conditions. Unlike space missions, which often capture global attention and funding, ocean expeditions tend to operate quietly, funded by limited budgets and often overlooked by governments and the public. Space exploration is glamorous. It inspires visions of rockets, astronauts, and alien worlds. Ocean exploration, despite being just as exotic, struggles to capture the same excitement. As a result, funding for deep-sea research lags far behind. Many projects are underfunded, limited in scope, and unable to repeat voyages often enough to build a complete picture. Scale makes the challenge even greater. The ocean is vast. It covers more than 360 million square kilometres. Mapping it in detail with sonar would take centuries if only a few ships were at work. And while the number of research vessels has grown, it's still nowhere near what's needed to cover the ocean at the same level of detail as land. To make matters more challenging, conditions on the surface aren't always cooperative. Storms, waves, and unpredictable weather can delay or cancel expeditions. Unlike satellites in orbit, research ships must navigate the elements, and the elements don't always allow for easy work. Then there is the human factor. The deep sea is not a friendly environment. Humans can't dive far without specialised equipment, and most of our attempts to go deeper than a few hundred metres require machines. Only a handful of crewed submersibles in history have reached the deepest parts of the ocean, and those missions are rare. The famous descent to the bottom of the Mariana Trench by Jacques Piccard and Don Walsh in 1960 was followed by only a few similar expeditions over the next half-century. More recently, filmmakers and explorers like James Cameron have returned, but these remain exceptions. Unlike airplanes, which crisscross the sky daily, deep-sea submersibles are deployed only occasionally, and most ocean research is carried out by robotic vehicles. That makes sense for safety and cost, but it means exploration is slow, cautious, and dependent on limited opportunities. There's also an imbalance in priorities. Human curiosity is broad, but funding tends to follow headlines. Space has become the dominant frontier in science fiction, in public imagination, and in government policy. Mars rovers, lunar missions, and telescopes looking back to the Big Bang receive billions of dollars and global attention. Meanwhile, deep-sea exploration is often considered secondary. It doesn't always come with the same political or cultural prestige, even though the discoveries can be just as profound. The irony is that in many ways, exploring the deep sea is easier than exploring space. It doesn't require leaving Earth, surviving vacuum, or travelling light years. But the way humans assign value and resources means space exploration races ahead, while the deep sea waits quietly in the dark. Psychology plays a role as well. The deep sea inspires fear. Humans are land animals, adapted to air and open space, not confined darkness and crushing pressure. Stories of shipwrecks, drownings, and sea monsters reinforce the sense that the ocean is dangerous and inhospitable. While astronauts are celebrated as heroes for travelling into the void of space, deep-sea explorers are fewer, often less recognised, and face risks that feel less glamorous but no less real. Fear of the unknown keeps many people from even considering the ocean as a place for adventure, and that cultural hesitation has consequences for how much effort we dedicate to exploration. Another reason why so little has been explored lies in the difficulty of gathering information. In space, a telescope can collect light from distant stars and produce mountains of data without leaving Earth. In the ocean, data is harder to gather. Sonar mapping requires time-consuming sweeps back and forth. Samples must be brought up carefully, often damaged or altered by the pressure change. Fragile deep-sea creatures sometimes collapse when removed from their environment, making it difficult to study them in laboratories. The result is that even when expeditions succeed, the amount of information collected is small compared to the vastness of the ocean. Progress is slow, not because of lack of will, but because of the nature of the environment. And yet, despite all of this, the real challenge is that we've simply only just begun. Human civilization has been using telescopes for centuries, but deep-sea technology is relatively young. The first reliable submarines appeared less than 100 years ago. Advanced ROVs and AUVs are only a few decades old. Modern sonar mapping capable of producing high-resolution images of the seafloor is even younger. In many ways, ocean exploration is still in its infancy. What feels like neglect is partly just the slow timeline of technology catching up to curiosity. In another 100 years, with better machines, cheaper sensors, and broader interest, we may look back and see that this was the age when ocean exploration truly began. When you bring all of these factors together, the picture becomes clear. The deep sea is vast, hostile, and expensive to explore. Technology has only recently become capable of probing it. Funding is limited, and public interest is easily pulled toward other frontiers. The result is that less than 5% of the ocean has been directly studied. But that 5% has already revealed wonders. It has shown us creatures we never expected, ecosystems that thrive without sunlight, landscapes as dramatic as anything on land. Which leads to an obvious question. If this is what we've discovered from only a fraction, what secrets are waiting in the other 95%? And as we consider that question, the next step is to look more closely at the obstacles themselves. Among the greatest of these is one invisible barrier, one that begins pressing down the moment you descend beneath the waves. Pressure is the unseen wall that keeps us from venturing deeper, and it may be the single most important reason why so much of the deep sea remains a mystery. Pressure is one of those forces that we rarely think about because we live with it constantly, but it's also one of the most unforgiving barriers nature has ever put in place. On land, we move freely, and we don't feel the air pressing down on us even though an entire atmosphere rests above our heads. Our bodies are built to withstand it, to the point where we never notice. Step into the ocean, however, and the story changes quickly. Pressure increases at a rate that's both predictable and astonishing. Every 10 meters you descend adds another full atmosphere. At 20 meters, it's like having 2 Earths worth of air stacked above you. At 50 meters, it's 5. At 1,000 meters, it's 100. Go to the deepest trench, more than 11,000 meters down, and the pressure is over 1,000 times greater than what you feel standing in your room right now. That number is hard to imagine, but picture this. It's like balancing the weight of a small car on every square inch of your body. No human, no ordinary machine can survive that without protection. Divers know the limits of pressure well. Recreational divers rarely go deeper than 40 meters. Even with training, special gases and advanced gear, human divers struggle to pass a few hundred meters. Beyond that, the pressure crushes lungs, blood chemistry shifts dangerously, and nitrogen dissolves into tissues with lethal consequences. The physiology of the human body is simply not designed for such environments, which means that almost all of the deep sea is off limits to direct human presence. We can look at it through machines, but we can't live there. We can't swim there. We can't even survive for minutes without catastrophic failure. Pressure is not just a challenge, it's a hard wall that only technology can help us cross. Machines face similar problems. Submarines must be designed like fortresses, with thick hulls that resist compression. A small flaw in the design, a crack in the metal, or a failed seal can lead to catastrophic implosion. Engineers spend years perfecting the curves and materials of deep-sea submersibles so that they distribute pressure evenly. Even then, only a handful of crewed submarines in history have reached the deepest parts of the ocean. The Trieste in 1960, James Cameron's Deep-Sea Challenger in 2012, and a few specialised vessels since then. Each dive required massive investment, painstaking preparation, and enormous risk. These are not everyday machines. They're unique, built at great expense, operated by highly trained teams and used sparingly. Remotely operated vehicles help overcome some of the risk, but they too must withstand pressure. At depths of several kilometres, cameras, lights, robotic arms and electronics all sit inside pressure-resistant housings. Designing these housings is a challenge in itself. They must be strong enough to resist crushing forces, but also light enough to allow mobility. They must carry instruments sensitive enough to record data without being destroyed by the environment. They must survive not just the pressure, but the cold, the corrosion of salt water, and the total darkness that requires artificial lighting for every image. Pressure becomes the invisible test of every design, the gatekeeper that decides whether our machines will function or fail. It's not just the machines that struggle. Samples collected from the deep often cannot survive the journey back to the surface, because pressure itself is part of their environment. Many deep-sea creatures are adapted to live under immense pressure, and when brought up they collapse, expand or die before they can be studied. Soft-bodied animals lose their shape, gas-filled structures burst, and entire ecosystems break down because the conditions they rely on vanish. Scientists have developed pressurized containers to keep samples intact, but these are complicated and expensive. The result is that much of what we know about deep-sea life comes from brief glimpses rather than long-term study. Pressure not only keeps us out, it also keeps its secrets in. For humans, the numbers associated with pressure are almost beyond comprehension. At the bottom of the Challenger Deep in the Mariana Trench, pressure reaches more than 1,086 bars, equivalent to about 16,000 pounds per square inch. To put that in perspective, imagine the weight of 50 jumbo jets pressing down on a single person. Yet life exists there. Microbes, amphipods, and even fish have been found at incredible depths, surviving under conditions that would crush anything unadapted. Their biology is astonishing, built not in spite of the pressure but because of it. Their cell membranes are reinforced with special molecules, their proteins are structured to resist deformation, and their bodies lack gas-filled cavities that would implode. Pressure for them is not an obstacle but a natural part of existence. For us, however, it remains an almost insurmountable barrier. Part of what makes pressure such a relentless force is that it increases predictably. It doesn't fluctuate. It doesn't vary with the weather or the tides. It simply builds with depth, and no technology or clever trick can change that. We can only build to resist it. And the deeper we go, the stronger it gets, until even the strongest materials reach their limits. Engineers are constantly searching for better alloys, composites, and structural designs to push deeper, but every improvement comes with higher costs, which is why so few machines have gone all the way down. The ocean is vast and pressure ensures that only tiny areas have been explored. When people compare the challenges of space and sea, pressure is one of the clearest differences. In space, the main obstacle is vacuum, but vacuum is absence. You can build a sealed cabin, and as long as it doesn't leak, it can hold. In the deep sea, the obstacle is overwhelming presence. The water presses in from every side with unrelenting force. A spacecraft in orbit can last years. A submersible at full ocean depth lasts hours, maybe days before it must surface for safety. Pressure doesn't allow casual exploration. Every dive is a race against time, equipment fatigue, and the possibility of catastrophic collapse. The psychological effect of pressure should not be underestimated either. Even in relatively shallow submarines, crews are aware that a hull breach would be fatal. The knowledge that thousands of meters of water rest above you, ready to crush instantly if anything goes wrong, weighs on the mind. It's part of why so few crewed missions are attempted. Machines feel no fear, but humans do, and pressure amplifies that fear. Every groan of metal, every creak of the hull, reminds explorers of the invisible wall pressing down from all sides. That tension adds another barrier to exploration, one that doesn't appear on technical charts, but influences decisions nonetheless. Despite all of this, engineers and scientists have not given up. They've built pressure-resistant cameras, sampling devices, and autonomous vehicles that push deeper with every generation. Advances in materials science hold the promise of stronger, lighter submersibles. New approaches, such as flexible housings and adaptive designs, aim to make machines that don't just resist pressure but adapt to it. Some researchers even study deep-sea animals to borrow their strategies, hoping to build technology that mimics biology's solutions. Step by step, dive by dive, pressure is being challenged. But for now, it remains the single greatest reason why most of the deep sea lies beyond our reach. And yet, pressure is only one part of the problem. Even if we build machines that can survive it, another challenge waits. Once you descend far enough, sunlight disappears and the ocean transforms into an endless midnight. Darkness, just as much as pressure, is part of what makes the deep sea an unknown world. Pressure may be the wall that keeps us out, but once you manage to build a vessel strong enough to survive it and descend into the depths, you meet another barrier that's just as absolute. Darkness. Sunlight is a constant companion in our daily lives. We wake to it, measure our days by it, and rely on it not just for warmth, but for the rhythms of everything we do. In the ocean, that light only goes so far. It penetrates down to around 200 meters before fading into what scientists call the twilight zone. Beyond that, the ocean becomes a realm of perpetual night. It's not dim in the way a late evening feels dim. It's a total absence, a blackness so complete that the human eye can never adjust to it. Once you reach the deep ocean, there is no dawn, no moonlight, no stars, only the endless midnight zone. For creatures that live there, darkness is normal. For humans, it's unsettling. We're used to sight being our primary sense. We depend on it for nearly everything. But in the deep sea, sight becomes almost useless without artificial help. Explorers who send cameras down or ride in submersibles describe the experience as floating through a void, a space where the boundaries are invisible and the only thing that exists is what your lights reveal. And those lights can only reach a few meters before being swallowed by the black. It's like driving down a road on a moonless night with your headlights illuminating just enough to see forward, but with no ground, no horizon, no sky to orient you. The sense of scale, of distance, even of direction disappears. That endless night makes exploration challenging in ways we don't always think about. Cameras require light, and light requires energy. Powerful lamps must be carried by submersibles, but the deeper you go, the more the light scatters and fades. You can light up a patch of seafloor, but you'll never flood the landscape in brightness the way the sun does. You'll always be seeing fragments, tiny windows into an infinite dark, and that means even when we send machines down, our vision is narrow and limited. The ocean refuses to show itself all at once. It offers only glimpses, and only to those willing to bring their own light. Darkness doesn't just challenge machines, it defines ecosystems. Without sunlight, there are no plants as we know them. Photosynthesis is impossible. Instead, life depends on two alternatives. One is chemosynthesis, where microbes near hydrothermal vents use chemical energy from the Earth itself to build food chains. The other is a rain of detritus, tiny particles of organic matter falling from above. Scientists call it marine snow, a slow drift of remains from surface waters, feeding the deep in a delicate trickle. In this way, the darkness shapes not just how creatures see, but how they live, eat, and evolve. To cope with the absence of light, many deep-sea animals have developed remarkable adaptations. Some have enormous eyes, wide enough to capture the faintest glimmer, even the traces of bioluminescence from other creatures. Others have dispensed with eyes entirely, relying on touch, vibration, or chemical cues to navigate and hunt. Many have evolved to produce their own light. Bioluminescence is one of the most widespread and fascinating phenomena in the deep sea. Tiny chemical reactions within cells produce glows, flashes, or patterns of light. Some use it to lure prey, others to communicate, and still others to confuse predators. To a human observer, it's like drifting through a silent fireworks display, sparks of blue and green against the black. For the creatures themselves, it's language, survival, and strategy. From the perspective of exploration, darkness also complicates mapping. On land, satellites use light to photograph terrain. In space, telescopes use light to capture distant galaxies. In the ocean, once you pass beyond the sun's reach, that tool is gone. Instead, we rely on sound. Sonar pings bounce off the seafloor and return, giving us outlines and shapes. But sound doesn't reveal colour or texture the way light does. It gives us geometry without detail, shadows without clarity. It's useful, but it doesn't replace vision, which means that much of what we know about the deep ocean floor comes from sound images, not direct sight. The true appearance of most of it remains unseen. Darkness has another consequence. It isolates. Creatures and ecosystems deep below live cut off from the rhythms of the surface world. Tides and currents reach them, but sunlight and moonlight do not. Time itself feels different there. Without day and night cycles, life follows other patterns. Some animals drift slowly for years, others live for centuries, all in a timeless shadow. For humans, visiting that environment feels alien. We're so tied to the passage of day and night that entering a world where those markers don't exist disorients us. Submersible pilots describe losing their sense of time, unsure whether minutes or hours have passed in the blackness. Darkness bends not just visibility but perception itself. And yet, as forbidding as it is, darkness also hides beauty. The flashes of bioluminescence, the slow pulse of jelly-like creatures, the ghostly outlines of strange fish drifting by, all create a sense of wonder. Every expedition that pierces the black returns with images that seem otherworldly. That wonder fuels curiosity, but it also emphasizes how little we've seen. If each glimpse reveals something extraordinary, how much more lies out there, invisible in the unlit expanse? Darkness guards those secrets as effectively as pressure, perhaps even more so because unlike pressure, it cannot be resisted. You can build walls against crushing force, but you cannot create sunlight where none exists. You can only bring lamps, and lamps will never illuminate an entire ocean. One of the striking facts about this midnight zone is that it makes up the majority of Earth's living space. Most of the biosphere is in permanent darkness, yet humans evolved in sunlight and still live almost entirely within its reach. We're diurnal creatures tied to the surface. That mismatch means that most life on Earth exists in conditions we barely understand. To study those conditions requires machines that carry light into the dark, and every beam reveals something unfamiliar. We've sent probes into space expecting to find alien life, but in truth, the aliens live among us, in the deep ocean, shaped by an environment of eternal night. It's worth considering how darkness influences not just biology but also our imagination. Myths of sea monsters often grew out of fear of the unseen. When something vast and unknown stirs beneath the surface and no one can see what it is, the mind fills the void with terror. Even today, the idea of the deep ocean unsettles many people. The thought of being surrounded by blackness, with unseen creatures moving nearby, stirs a primal fear. Darkness represents the unknown, and the unknown triggers caution. That psychology, just like pressure, adds another layer to why so little of the deep sea has been explored. It doesn't just challenge our machines, it challenges our courage. For scientists, however, the darkness is less a terror and more a puzzle. How do you record life without disturbing it with artificial light? Many deep-sea creatures are sensitive to brightness. A sudden lamp can frighten them away or alter their behaviour. To truly study them, scientists design low-light cameras, sensitive detectors, and even lights that mimic bioluminescent glows. Exploration becomes a careful negotiation between visibility and preservation. Shine too much light, and you disrupt the ecosystem. Shine too little, and you see nothing. The balance is delicate, and it reminds us that we're visitors in a world that doesn't belong to us. Darkness also complicates navigation. On the surface, we use stars, GPS, and landmarks. In the deep sea, there are no stars, no satellites that penetrate the water, no landmarks that can be easily identified. Submersibles rely on sonar, inertial navigation, and acoustic beacons, but even then they often drift, lose orientation, or must be carefully guided by ships above. Moving through the darkness is slow, uncertain, and meticulous. Every meter gained is an effort, every discovery a small victory. This pace of exploration is another reason why progress is so limited. The darkness enforces slowness, and yet, despite all of these barriers, humans continue to venture into the midnight zone. Every dive returns with stories, images, and samples that remind us how rich the unknown really is. Darkness may be an obstacle, but it's also what preserves the mystery. Without it, the deep ocean would not hold the same allure. It's the unlit vastness that keeps our curiosity alive, that ensures we always feel there is more to learn. But the ocean doesn't stop at darkness. Along with pressure and the absence of light comes another factor that shapes the deep and challenges our ability to explore. Once you descend far enough, temperatures drop, and the sea becomes a realm of near freezing cold. That cold, combined with pressure and darkness, forms the trio of obstacles that define the deep. And to understand why exploration is so limited, we need to look at how cold reinforces the mystery of the abyss. Pressure crushes, darkness blinds, but as you descend into the deep, another force slowly but relentlessly shapes everything: the cold. If you've ever swum in the ocean on a summer day and felt the sudden chill when you dive below the surface, you've had the faintest taste of it. The deeper you go, the colder it becomes, until the water stabilizes at temperatures just above freezing. In most of the deep ocean, it hovers between 1 and 4 degrees Celsius, cold enough that without protection, a human body would quickly lose heat and drift toward hypothermia. Down there, cold isn't just a background condition. It's the environment itself, a constant, inescapable presence that dictates how life survives and how exploration must be carried out. The cold is deceptive because water doesn't feel hostile in the same way pressure does. It doesn't crush you instantly. It doesn't loom like darkness. Instead, it saps heat slowly, steadily, and without mercy. A diver in tropical waters can feel warm at the surface, but within minutes of descending, the chill becomes unmistakable. At greater depths, survival time is measured not in hours but in minutes if you're unprotected. The ocean's cold is a thief of energy, and no matter how tough you are, biology alone cannot withstand it. That's why every submersible must be insulated, every machine must be designed to operate in near-freezing conditions, and every plan for exploration has to account for how cold influences both humans and technology. Cold also changes the properties of water itself. At lower temperatures, water becomes denser, currents shift, and chemistry slows. Reactions that proceed quickly in warm environments drag in the abyss. For machines, this means lubricants thicken, batteries discharge less efficiently, and materials become brittle. Engineers have to design equipment that functions as reliably in near-freezing water as it does in laboratories on land. That's harder than it sounds. Electronics don't like cold. Mechanical systems seize up. Lights dim. The ocean's chill seeps into everything, and resisting it requires layers of protection that add bulk and cost to every design. Life, however, has adapted in remarkable ways. Many deep-sea creatures thrive in temperatures that would paralyze or kill most organisms at the surface. Their enzymes, the tiny biological machines that drive metabolism, are built to function efficiently at low temperatures. Their membranes remain fluid despite the cold. Some species produce antifreeze proteins that prevent ice crystals from forming in their bodies. Others simply move slowly, their entire existence adapted to a pace dictated by the cold. This is one reason why deep-sea creatures often seem sluggish when observed. It's not that they lack energy, it's that energy is conserved carefully, because in such a cold environment, every calorie matters. That slowness shapes entire ecosystems. Growth rates are reduced, reproduction is infrequent, and lifespans are extended. Some deep-sea corals are thousands of years old, growing millimetre by millimetre in the cold darkness. Fish and crustaceans can live decades longer than their shallow water relatives. Even microbial communities operate at a slower tempo, breaking down organic matter over centuries rather than days. Time itself feels stretched in the cold. For us, accustomed to the rapid cycles of surface life, this seems almost alien. but for the inhabitants of the abyss it's normal. Cold isn't an obstacle, it's the foundation of their world. For explorers though, cold complicates everything. Humans lose heat 25 times faster in water than in air. That's why even moderately cool water can be deadly in surprisingly short periods. Specialized suits protect divers, but those suits are bulky, limit mobility, and still impose time limits. For machines, insulation and heating systems are required, draining precious power. The deeper the dive, the more the cold asserts itself, slowing systems, testing endurance. Unlike pressure, which can be engineered against with strong materials, or darkness, which can be countered with lamps, cold is pervasive. It seeps into every joint, every circuit, every cell. It's not a force you block. It's one you must constantly resist. Cold also influences chemistry in ways that affect exploration indirectly. Gas solubility increases at lower temperatures, meaning the deep ocean holds more dissolved gases like oxygen and carbon dioxide. That shapes the biology of deep-sea creatures, but also influences how samples behave when brought to the surface. Organisms adapted to high oxygen levels may struggle in warmer lab environments. Samples preserved at surface temperatures may degrade rapidly. Scientists must carefully control conditions to keep specimens intact, often using chilled tanks or pressurized containers to mimic the abyss. Without these precautions, the mysteries they bring back can vanish before they can be studied. It's not surprising then that cold is often underestimated by the general public. People focus on pressure and darkness, the dramatic barriers. Cold feels more mundane, but in truth, it is just as formidable. The fact that almost the entire deep ocean sits at a constant near-freezing temperature is extraordinary. Imagine if the surface world were locked in permanent winter, where every forest, mountain and plain never saw warmth above a few degrees. That's what the deep ocean is like. It's a frozen realm without ice, a liquid winter that stretches across most of the planet. And yet, life finds a way to flourish there. From an evolutionary standpoint, cold has driven adaptations that seem bizarre to us. Some fish have translucent bodies, conserving energy by not producing pigments. Others generate antifreeze proteins in their blood, preventing ice formation even when currents bring supercooled water from polar regions. Many deep-sea animals grow slowly to enormous sizes, a phenomenon scientists call deep-sea gigantism. It's thought that cold temperatures and high pressure contribute to this trait, allowing certain species to reach lengths far greater than their shallow water relatives. The result is creatures like giant isopods, massive amphipods, and squids that stretch longer than cars. Without the cold, these life strategies might never have evolved. For exploration, though, the challenge is clear. Machines must survive not just crushing pressure, but the constant drain of low temperatures. Lights, cameras, and robotic arms must work flawlessly in conditions that test every material. Power systems must endure without failing, and above all, expeditions must prepare for the fact that once you send something into the abyss, it is entering a world where every second is influenced by cold. The ocean does not forgive shortcuts. It demands designs that anticipate the freeze. Cold also limits human endurance in indirect ways. Even on research ships at the surface, scientists working in polar regions face freezing winds, icy decks, and relentless chill. Deploying instruments in such environments is exhausting. Handling samples in near-freezing water numbs fingers, slows reflexes, and increases the risk of accidents. Cold is not confined to the depths. It radiates outward into the process of exploration itself, shaping the experience long before the first dive begins. When you consider pressure, darkness, and cold together, you begin to see why the deep sea has remained so unexplored. Each one alone would be a significant barrier. Together, they form a near impenetrable triad, a constant reminder that this is a world apart. And yet, despite all three, we continue to explore, because every time we manage to pierce those defenses, we discover something astonishing. Cold doesn't just hinder us, it creates conditions for life and landscapes that defy expectation. The challenge only makes the discoveries more valuable. And this is where the scale of the ocean itself reasserts its presence. It's not just the physical conditions that keep us out. It's the sheer vastness of it all. Even if we had machines perfectly designed to resist pressure, light up the darkness, and shrug off the cold, we'd still face the problem of distance and size. The ocean is too big, too deep, too sprawling to ever be fully known all at once. Which brings us to the next obstacle in our journey, the challenge of distance and scale, and why reaching the deep sea is harder than most people imagine. Pressure weighs down, darkness blinds, cold freezes, but even if all of that could somehow be managed, another truth remains. The deep ocean is enormous. Its scale is almost beyond comprehension, and that sheer size is one of the greatest barriers to understanding it. When we talk about exploration, we sometimes picture it as a matter of reaching a single destination, a mountain summit, a cave, a planet. The deep sea, however, isn't a single destination. It's an entire world spread across hundreds of millions of square kilometers. The ocean covers more than 70% of Earth's surface. That's about 360 million square kilometers of water. Beneath that water lies a seafloor more expansive than all the continents combined. Exploring it is not like climbing a mountain. It's like trying to map an entire planet from scratch. To put the numbers in perspective, think about this. If you took all of the Earth's land surfaces, every desert, forest, mountain and city, and combined them, you'd still fall short of the area covered by the oceans. That means most of the planet is underwater terrain we can't easily access, and unlike land, which we can cross with vehicles, roads and planes, the ocean demands a different approach. You can't just drive across it or fly above it and expect to see what lies beneath. Every meter must be probed with sonar, cameras or sensors. Every descent must be carefully planned. Covering even a small fraction of that vastness requires immense time and resources. Scale doesn't only mean area, it means depth as well. The average depth of the ocean is about 3,700 meters, more than 2 miles. Imagine that everywhere you look, the ground begins several kilometers down, hidden beneath water. And then remember that the deepest points, like the Mariana Trench, plunge to more than 11,000 meters. If Everest, the tallest mountain on land, were placed inside, its peak would still be covered by nearly 2 kilometers of water. The vertical dimension of the ocean adds another layer of scale that makes exploration harder. You don't just move horizontally across a flat surface. You descend into an abyss that grows more hostile the deeper you go. It's like trying to explore an entire continent that has its floor hidden beneath a massive canyon. For explorers, this scale translates into time. Mapping the seafloor with sonar involves sending sound waves downward and waiting for them to return. A single ship moving back and forth in a grid pattern can take months to cover an area the size of a small country. At the current rate of mapping, it would take centuries to produce a complete high-resolution map of the ocean floor. And even then, a map would only reveal shape, not detail. Life, ecosystems and geology would still need direct observation, sample collection, and repeated dives. Each of those steps multiplies the time needed. Distance also complicates logistics. Reaching remote parts of the ocean requires ships that can operate for weeks without resupply. Research vessels must carry fuel, food, and spare parts for their crew and machines. They must navigate storms, unpredictable weather, and long travel times just to arrive at a target site. Once there, they must carefully deploy equipment, recover it, analyze data, and often repeat the process. A single expedition might return with only a handful of useful dives, each covering a tiny patch of seafloor. Multiply that against the size of the ocean, and it becomes clear why exploration feels so incomplete. Another aspect of scale is cost. The larger the area, the more resources are needed to study it. Fuel for ships, salaries for crew, maintenance for equipment, all of it adds up quickly. Governments and research institutions must decide where to allocate funds, and often space missions or terrestrial projects win out because they promise more visible results. The ocean, vast and hidden, struggles to compete for attention. Its size works against it, not just physically, but politically and economically. Scale also hides complexity. The seafloor is not uniform. It's not a flat plain waiting to be surveyed. It's covered with ridges, trenches, volcanic vents, canyons and mountains. The Mid-Atlantic Ridge, for example, is longer than any mountain range on land. Hydrothermal vent fields can be as small as a football field, but harbour unique ecosystems unlike anything else on Earth. Abyssal plains stretch for thousands of kilometres, yet even those plains hold subtle variations in sediment, chemistry and biology. Exploring one site tells us nothing about the site next door. Every location is unique, and that uniqueness multiplies the scale of the task. To truly understand the deep sea, we'd have to study countless environments, not just a few representative samples. The distance to these environments creates another layer of challenge. Unlike space, where telescopes let us see faraway galaxies, the ocean hides everything beneath a shield of water. Satellites can hint at seafloor features by measuring surface height variations, but those are blurry outlines, not details. To get real data, you have to go there physically. That means thousands of expeditions scattered across the globe, each targeting different locations. The ocean's size makes such coverage unlikely in any short time frame. That's why, even now, most deep-sea features remain unnamed, unmeasured, and unstudied. It's worth remembering that scale doesn't just apply to geography, it applies to biology too. The number of species in the deep ocean is unknown, but estimates suggest millions remain undescribed. Each expedition brings back organisms new to science, sometimes dozens at a time. If less than 5% of the ocean has been explored, that means the vast majority of its species remain hidden. The scale of biodiversity is staggering, and cataloguing it would take lifetimes. It's like walking into a vast library where almost every book is unread, every shelf unmarked, and the collection is larger than anything you could ever finish. Distance adds to the psychological barrier as well. When we think of exploration, we often imagine journeys we could theoretically take ourselves, hiking through a forest, flying to another city, climbing a mountain. But the deep ocean feels remote, detached from our everyday lives. Few people will ever see it firsthand, and that sense of remoteness makes it harder to connect with emotionally. It feels far away even though it begins just beneath the surface. That paradox, closeness in geography but distance in accessibility, is part of what keeps it mysterious. Scale also creates vulnerability. Because the ocean is so large, monitoring it for changes is difficult. Climate shifts, pollution, and human impacts can spread unnoticed for decades because we lack the coverage to see them. By the time we detect changes, they may already be widespread. The sheer size of the ocean means it hides not only its natural mysteries, but also the consequences of our actions. That makes exploration urgent, yet the scale slows progress, creating a constant tension between need and ability. And yet, despite the enormity of the challenge, exploration continues in small steps. Each expedition covers a little more ground, adds a few more data points, maps a few more ridges. Advances in technology are helping. Autonomous vehicles can cover more area without human crews. Swarms of drones may one day map large sections simultaneously. Satellites improve at detecting subtle signals that hint at what lies below. Progress is slow, but it accumulates, like drops filling a vast basin. When you combine all these factors, the reality becomes clear. The deep sea is not unknown because of lack of interest. It's unknown because of its immense size and depth, because every attempt to study it is like shining a flashlight into a cavern the size of the Earth. No matter how powerful the beam, the darkness beyond remains, and as long as that scale exists, exploration will always lag behind curiosity. Which brings us to the next layer of the problem. Even if you could overcome distance and size, even if you had ships and machines scattered everywhere, the technology itself still struggles. The ocean's conditions strain every invention we've built. Submarines, ROVs and sensors all face limits that remind us that our tools are still young compared to the challenge. And so, as we continue, the question becomes clear: how exactly do our machines fall short when faced with the demands of the deep? Distance and scale make the deep sea feel impossibly vast, but even if you narrowed down the areas worth exploring, you'd still face the stubborn reality of our tools. Technology has opened doors, but it hasn't solved everything. Submarines, remotely operated vehicles and autonomous machines are marvels of engineering, yet they remain limited in ways that define how much we can actually learn. It's tempting to think of technology as a universal answer, the kind of magic that overcomes any barrier with enough innovation. But in the deep sea, every tool comes with constraints, compromises, and fragility. And those limitations explain why progress feels so slow. Crewed submarines were the first serious attempt to push human presence into the abyss. These machines are designed to carry people into an environment that would otherwise be instantly fatal. Their hulls must resist pressure thousands of times greater than what we experience on land. They must provide oxygen, remove carbon dioxide, regulate temperature, supply light, and maintain communication with the surface. All of this must fit into a compact vessel that can descend and rise reliably. The engineering challenge is immense, and for most of history, only a handful of submarines have managed it. The Trieste, which descended to the bottom of the Mariana Trench in 1960, remains one of the most famous examples. It was essentially a sphere of steel thick enough to keep 2 men alive at 10,000 meters, lowered slowly by cables and released ballast. That dive proved it could be done, but it was a one-off achievement, not the beginning of routine exploration. Decades passed before anyone returned to that depth. Modern crewed submersibles are more advanced. They use better alloys, stronger acrylic domes for observation, and improved life support systems. James Cameron's Deep-Sea Challenger, for instance, used specialised foam for buoyancy and a vertical design that allowed a single pilot to reach the deepest ocean. Yet even these advances show the limitations. A crewed submersible is expensive, slow, and risky. It requires years of development, extensive testing, and a support ship at the surface. Each dive may last only a few hours, after which the vessel must return to refuel, recharge, and prepare again. Only a few exist worldwide, and they are used sparingly. Unlike satellites that orbit continuously, or telescopes that operate for decades, crewed submarines are rare events, like special expeditions rather than ongoing programs. That's why much of the work has shifted to remotely operated vehicles, or ROVs. These are tethered machines controlled from the surface by teams of operators. They can be larger than cars, bristling with cameras, lights, robotic arms, and sampling devices. ROVs allow scientists to observe without risking human lives. They can spend longer in the deep, maneuver more flexibly, and carry tools that collect rocks, sediments, and biological specimens. The tether provides power and communication, making it possible to stream video in real time from the ocean floor to researchers on deck. In many ways, ROVs are the workhorses of modern oceanography. They've revealed hydrothermal vents, strange new species, and countless geological formations, but the tether itself is also a limitation. Long cables are heavy, prone to tangling, and vulnerable to currents. Deploying them requires careful coordination, often with winches and cranes that can fill the entire deck of a research vessel. ROVs can only travel as far as their tether allows, which means their range is constrained. Strong currents can drag the cable, straining the vehicle or forcing operators to abort dives. Recovery is slow, often taking hours, and every deployment risks damage. And because each ROV is linked to a ship, it can only operate in the small area beneath its support vessel. Covering wide regions requires repeated deployments, consuming time and resources. To get around these constraints, scientists have developed autonomous underwater vehicles, or AUVs. These machines operate without tethers, navigating through the deep on pre-programmed routes. AUVs can map large areas with sonar, measure chemical properties, and record data without needing direct control. When their mission is done, they surface and transmit data to the ship, or wait to be retrieved. In theory, fleets of AUVs could map the ocean much faster than single ROVs or submarines. They represent a promising future for exploration. Yet autonomy comes with trade-offs. AUVs are limited by battery life, often only a few hours or days before they must recharge. Communication is minimal, since water blocks most signals. Operators can't guide them in real time, so missions must be carefully planned, and if something goes wrong, the vehicle may be lost forever. Navigation is also difficult. Without GPS signals beneath the water, AUVs rely on inertial systems, acoustic beacons, or dead reckoning, all of which accumulate errors over time. A drift of even a few meters per hour can mean missing a target entirely. For mapping, that's acceptable. For studying specific creatures or vents, it can be a deal-breaker. Every type of machine also faces the same environmental challenges. Pressure strains housings, cold drains batteries and stiffens joints. Darkness forces reliance on artificial light, which requires power. Currents push vehicles off course. Salt water corrodes materials relentlessly. No matter how well designed, machines fail, and when they fail at depth, recovery is often impossible. Millions of dollars of equipment have been lost to the abyss, swallowed by the same conditions they were built to study. Each loss slows progress, not just financially but psychologically, making teams cautious about pushing limits. Even when machines work perfectly, their coverage is small. A camera may record stunning footage of a new species, but that's a snapshot of a few square meters of sea floor. Sonar may map an area, but it lacks biological detail. A sampling device may collect one or two organisms, but it misses the countless others nearby. Exploration is piecemeal, fragmentary. Unlike space telescopes that can survey entire galaxies, deep-sea machines work like flashlights, illuminating tiny patches while the rest remains hidden. That's why, despite decades of research, the percentage of the ocean studied remains so low. The tools are good but not yet transformative. Cost compounds the problem. Building a single ROV or AUV can run into millions of dollars. Operating it requires a specialized crew, a support ship, and weeks of sea time. Ships themselves are expensive, often costing tens of thousands of dollars per day to run. That means every expedition must justify its budget carefully. Governments and institutions can only afford a limited number of voyages, and private companies rarely invest unless there's a clear profit, such as in oil, gas, or mineral exploration. Scientific curiosity alone often struggles to fund the machines needed to satisfy it. Technology also struggles with preservation. Bringing deep-sea creatures to the surface without destroying them remains a challenge. Many collapse or die when pressure decreases. Even with pressurized containers, samples may not survive long enough to be studied properly. The result is that much of what we know comes from images and fragments, rather than full biological understanding. This isn't the fault of scientists or machines. It's simply a reflection of how fragile deep-sea life is when removed from its natural conditions. Despite all of these struggles, progress continues. Advances in materials, science promise stronger, lighter housings. Improved batteries extend mission times. Machine learning helps AUVs adapt to currents and obstacles. Miniaturization allows cheaper, smaller vehicles to operate in swarms rather than relying on single, expensive machines. New techniques like fiber optic tethers or laser communication may improve real-time control. Bit by bit, the limits are being pushed. But for now, the reality is clear. Our machines are still young, still clumsy compared to the scale and hostility of the deep ocean. They reveal wonders, but they also remind us of how much remains hidden. There's also a cultural struggle embedded in the technology question. Space exploration receives constant investment because it symbolises ambition, progress and discovery. Ocean exploration, while just as important, struggles to capture the same excitement. That lack of enthusiasm slows funding, which slows technological development, which in turn slows exploration. It's a feedback loop that keeps the deep sea mysterious. Technology could advance faster if more attention were given, but without attention, progress remains incremental. And so, we're left with a paradox. We have the tools to explore, but those tools are limited, expensive, and fragile. We've built submarines that can carry us to the deepest trenches, but only a handful of times. We've built ROVs that can map hydrothermal vents, but only in small areas. We've built AUVs that can roam untethered, but only for short periods before exhaustion. Each advance opens a window, but the window is small, and beyond it lies an ocean still untouched. Even so, these machines have transformed our understanding. Without them, we would know almost nothing of the deep. With them, we've glimpsed alien landscapes, discovered thousands of species, and revealed processes that reshape our view of life on Earth. The struggles are real, but so are the successes, and perhaps that's what keeps us pushing forward. The limitations remind us that mystery still exists, and mystery is part of what makes exploration worthwhile. But while technology defines what's possible, another factor decides what's prioritized. Machines can be built, ships can be launched, and discoveries can be made, but only if someone is willing to pay for it. Which leads us to the next barrier, one less visible than pressure or darkness, but just as decisive. Exploration is costly, and without funding, even the best technology sits idle. The ocean waits, but the question is whether we're willing to spend the resources needed to meet it. Technology may define what's possible, but funding decides what actually happens. The deep sea could be explored more thoroughly if more ships were deployed, more machines were built, and more expeditions were launched. Yet in reality, only a handful of dedicated research vessels are at sea at any given time, and most of them are limited by tight budgets. Exploration is expensive, and in the competition for resources, the ocean rarely wins. That's why so little of it has been studied, not just because of technical barriers, but because of financial ones. The cost of exploration is one of the quietest yet most decisive reasons the deep sea remains unknown. To understand why, it helps to picture what a single expedition actually involves. A research ship alone can cost tens of thousands of dollars per day just to operate. Fuel, crew salaries, maintenance, and supplies all add up. A voyage that lasts several weeks easily crosses into millions of dollars. Add to that the cost of equipment, ROVs, AUVs, sensors, sonar systems, pressurized sample containers, and the price grows further. Many of these machines are custom-built, tailored for specific missions, and repairing them after each dive is costly. Even something as simple as replacing parts requires specialized materials designed to withstand pressure and corrosion. Every element of deep-sea exploration is expensive, because nothing about it can be done cheaply or casually. The cost doesn't end when the ship returns. The data must be processed, samples must be studied, and findings must be published. That means paying teams of scientists, technicians, and students for months or years after the expedition itself. In many cases, the work of analysing results costs as much as the expedition that collected them. A single dive may yield thousands of hours of video and terabytes of sensor readings. All of it requires careful examination, and that requires funding. Exploration is not a quick strike. It's a long chain of investments that stretch far beyond the moment of discovery. So why not fund it more? After all, the ocean is critical to life on Earth. It regulates climate, produces much of our oxygen, and supports global biodiversity. The reason lies in how priorities are set. Governments, which provide the bulk of scientific funding, must balance defence, healthcare, infrastructure, education, and countless other needs. Ocean research, while important, often slips to the bottom of the list because it doesn't produce immediate or visible returns. A new bridge, a medical breakthrough, or a space mission captures public attention and provides clear benefits. A deep-sea expedition, no matter how fascinating, often feels abstract to those not directly involved. That lack of immediate relevance makes it harder to justify large budgets. Space exploration also competes directly with ocean research for funding and attention. Space missions are dramatic. Rockets launch in fiery displays. Astronauts wave from capsules. Telescopes reveal breathtaking images of distant galaxies. These events inspire and captivate, making them politically valuable. Ocean exploration, by contrast, happens quietly. A ship departs, a machine dives, and weeks later scientists announce the discovery of a new worm or fish. As remarkable as that is, it doesn't capture headlines in the same way. Politicians and the public tend to support projects that are visible, spectacular, and symbolic. The ocean's mysteries are profound, but they lack the spectacle that drives investment. Private funding also plays a role. Space has attracted billionaires and corporations eager to stake a claim in satellites, tourism, and resource extraction. The potential for profit drives investment. The deep sea, while rich in minerals and resources, is more difficult to exploit. Mining in the abyss is still experimental, fraught with environmental risks, and subject to international regulation. As a result, private companies are cautious. Without a clear path to profit, few are willing to spend the money needed for exploration. That leaves scientific institutions and governments carrying most of the burden, and their budgets are limited. The cost barrier also shapes how exploration is carried out. Instead of a global effort to map the ocean systematically, expeditions are scattered, funded piecemeal, and focused on specific projects. A team may receive a grant to study a vent field, another to map a trench, another to monitor a coral ecosystem. Each mission produces valuable data, but the efforts are fragmented. No single organisation has the resources to coordinate a comprehensive exploration of the entire ocean. That's why, even after decades of research, most of the seafloor remains blank space on our maps. It's not that there's no interest. Scientists are deeply motivated to explore the deep sea. Public curiosity exists too, as documentaries and films about the ocean often prove. But motivation without money cannot move ships. A vessel cannot launch on curiosity alone. It needs fuel, crew, and equipment, all of which must be paid for. That practical reality creates a gap between what we want to know and what we actually achieve. Some argue that the benefits of deep-sea exploration justify greater investment. The ocean holds potential for new medicines, as organisms adapted to extreme environments produce unique chemical compounds. It holds clues to climate change, since deep currents and sediments preserve records of Earth's history. It offers insights into biology, geology, and even the search for extraterrestrial life. Each discovery carries the possibility of reshaping science. Yet these benefits are long-term and uncertain. Politicians prefer projects that deliver clear results within election cycles. Funding ocean exploration often feels like planting seeds in soil, whose harvest will come far in the future. That disconnect slows investment, leaving much of the ocean unstudied. Even when funding is available, it is often short-term. Grants may last a few years, enough for one or two expeditions, but not long enough to establish permanent programs. Ships must then wait for the next round of funding, and research teams disband if new money doesn't arrive. This stop-and-start rhythm prevents the steady, systematic work needed to truly explore the ocean. Contrast this with space missions like the International Space Station, which receive continuous funding for decades. The difference in stability explains why progress in space feels more consistent than in the deep. Cost also affects equity. Wealthy nations can afford ships and submersibles, while poorer nations often cannot, even though many of them control vast ocean territories within their exclusive economic zones. This creates an imbalance where the ability to explore is concentrated in a few countries. Global cooperation could solve this. but cooperation itself requires funding and coordination, both of which are limited. The result is that large portions of the ocean, particularly around developing nations, remain unstudied simply because the resources aren't available locally. There's also a cultural element to funding. The ocean is seen by many as eternal, stable, and unchanging. That perception makes people underestimate its fragility. If the ocean seems endless, why spend millions studying it? But scientists know that the ocean is not static. It changes constantly, and human activity is altering it at unprecedented rates. Without exploration, we cannot track those changes properly. The lack of funding, therefore, doesn't just delay curiosity. It delays our ability to respond to crises, from collapsing fisheries to warming currents. Some efforts are being made to change this. International programs aim to map the entire seafloor by 2030, pooling data from many nations. Advances in cheaper autonomous vehicles are lowering costs. Partnerships between universities, non-profits, and governments are expanding coverage. Yet even with these efforts, the pace remains slow compared to the need. The cost barrier remains, and until it's addressed on a larger scale, most of the deep will remain mysterious. The irony is that the ocean itself provides resources that could justify the cost. Its role in regulating climate, absorbing carbon, and sustaining life is priceless. Without it, life on Earth would collapse. Yet because those benefits are invisible, spread across every breath of air and every drop of rain, they're taken for granted. We invest heavily in space because we dream of leaving Earth, but we underinvest in the ocean that makes Earth habitable in the first place. When you look at all of this, the conclusion is clear. The ocean is not unexplored because we lack the desire. It's unexplored because exploration is expensive and funding is scarce. Machines sit idle because no one pays to launch them. Ships remain in port because no one pays for fuel. Scientists wait for grants that may or may not arrive. The cost of exploration is not just measured in dollars, it's measured in the discoveries that never happen, the mysteries that remain unanswered, and the knowledge that slips away each year we delay. And yet, even with limited funding, the ocean has always drawn human imagination. The myths of monsters, the stories of lost ships, the fear of the unknown, all of these reveal how deeply the sea affects us. Cost may slow us, but curiosity persists. Which brings us to another part of the mystery. Beyond the financial and technological challenges, there is a psychological barrier as well. Fear. For centuries, humans have filled the deep with monsters and legends, symbols of what we can't see and don't understand. That fear, combined with cost and difficulty, continues to shape how we view the abyss. The cost of exploration is heavy, but money is not the only weight that keeps us from knowing the deep. Just as powerful, though less tangible, is the force of fear. The ocean has always stirred imagination, and imagination often leans toward the terrifying when confronted with the unknown. Pressure and darkness are invisible but real. Cold is steady and unavoidable. Scale is overwhelming. Yet none of those forces loom as vividly in the human mind as the things we imagine might be waiting for us in the abyss. Myths, monsters, and mysteries have always wrapped themselves around the sea, shaping how people think about it, and those cultural shadows still matter today. From the earliest seafaring stories, humans have described creatures rising from the deep to drag ships under. Giant serpents, enormous squid, dragons that coil through the waves, leviathans that dwarf any whale. Sailors returning from voyages often spoke of sightings, sometimes born of exaggeration, sometimes born of glimpses of real animals magnified by fear. A whale breaching suddenly beside a small wooden vessel could feel like a monster. A glimpse of a tentacle could be retold as a kraken. In times when navigation was uncertain and survival depended on fragile ships, the ocean felt like an enemy, alive and hostile, filled with threats both natural and supernatural. Those myths persisted for centuries, shaping how societies viewed the deep. The kraken became a symbol of the unknown, an image of tentacles stretching up from the darkness to pull entire ships into the black. Sea serpents were drawn on maps in places where cartographers admitted ignorance, their curling bodies a shorthand for unexplored waters. Stories of sirens, mermaids, and other hybrid beings reflected both fear and fascination, an acknowledgement that the ocean was not just a place of resources, but of mysteries beyond human understanding. For many cultures, the ocean was both a provider and a menace, a place that could give life and take it away without warning. These myths were not simply entertainment. They were survival tools, warnings embedded in story form. To speak of monsters was to teach caution, to remind sailors of the risks of venturing too far or straying into dangerous waters. Even now, the echoes remain. Popular culture continues to fill the deep sea with imagined giants, from colossal squids to ancient beasts sleeping in trenches. Movies and books bring those fears to life, sometimes exaggerating them to the point of fantasy, sometimes grounding them in the real possibility that enormous creatures might exist in places we've never looked. The line between myth and science blurs, because in the deep ocean, what we don't know is still far larger than what we do. Fear of the deep is not only about monsters, though. It's also about the environment itself. Imagine being lowered in a submersible, watching the light fade until nothing is visible outside but blackness. The pressure outside could crush steel. The temperature hovers near freezing. The silence is absolute, broken only by the groan of the hull and the hum of machinery. Even without monsters, the setting itself feels hostile, alien, and unforgiving. It's not difficult to understand why many people feel unease at the thought of descending. The fear is instinctive, rooted in survival. Humans evolved on land, in sunlight, breathing air. The deep sea is the opposite of all those conditions. It's no wonder that for many it feels like the last place we should go. This psychological barrier has practical consequences. Exploration requires not just machines and money, but people willing to design, build, and operate them. If the ocean inspires more fear than wonder, fewer people are drawn to devote their lives to studying it. Careers in oceanography require long voyages, time away from home, and the acceptance of danger. Funding agencies must also be convinced that projects are worthwhile, and cultural fear can influence those decisions. If the public views the deep as a place of terror or irrelevance, they are less likely to support exploration. In that way, myths and fears have shaped not just imagination but also policy. And yet, fear is not purely a barrier. It is also a motivator. The possibility of monsters has driven curiosity as much as it has discouraged it. The idea that something vast and unknown might lurk in the trenches has inspired expeditions, films, and scientific studies. The search for the giant squid, once thought to be purely mythological, eventually confirmed its existence through photographs and video. It was not a monster dragging ships under, but it was real, and it was enormous. Fear transformed into discovery. That process continues, as scientists still wonder what other large animals might inhabit the depths unseen. The deep sea's fearsome reputation keeps it in the imagination, ensuring that curiosity never fully fades. There's also a symbolic dimension to these fears. The ocean has always represented the unknown in human culture, a mirror for our own anxieties. To journey into the deep is to face what we don't understand, what we can't control, and what might threaten us. Myths of sea monsters often reflected broader fears of death, of chaos, of nature's power. In modern times, they sometimes echo concerns about technology, environmental change, or the limits of human ambition. The monsters we imagine in the deep are often projections of ourselves, our worries, and our limits. Even for scientists, the deep sea can stir unease. Submersible pilots often describe a heightened awareness of danger during dives. Every creak of the hull, every flicker of the lights, reminds them of the vast pressure outside. The knowledge that a single failure could mean instant death is a psychological weight that shapes how missions are planned and carried out. Safety is paramount and caution is constant. That caution slows progress, but it also ensures survival. Fear, in this sense, becomes a necessary ally, a reminder of the stakes and a guardrail against recklessness. But fear can also distort perception. For centuries, myths of monsters kept people from looking more closely, assuming the unknown was inherently dangerous. In some ways, that mindset still lingers. Popular culture often portrays the deep as a place of horror, filled with creatures designed to shock and unsettle. While those depictions capture attention, they also reinforce the sense that the ocean is frightening rather than fascinating. Scientists work to balance that perception, showing that while the deep holds strange and sometimes eerie life forms, it is also full of beauty, adaptation, and resilience. Changing the narrative from monsters to marvels is part of making the ocean feel less distant and less terrifying. Even with changing narratives, fear continues to play a role in why exploration is limited. It combines with cost, technology, and scale to create hesitation. Pressure, darkness, and cold are real barriers, but fear is a human barrier, one that influences decisions at every level. It is not written in physics, but in psychology. Overcoming it requires not machines, but stories, education, and perspective. By reshaping how we talk about the deep, by replacing myths of monsters with knowledge of ecosystems, we can slowly shift fear into curiosity. Yet perhaps it's also good that fear remains. Without it, the deep sea might already have been exploited recklessly, its ecosystems damaged before we even understood them. Fear has slowed us, but in slowing us, it may have preserved mysteries long enough for us to approach them more responsibly. The unknown is frightening, but it is also precious. The myths of monsters, in their own way, have helped protect the deep from human intrusion. And so, as much as fear shapes our hesitation, it also ensures the deep remains mysterious. That mystery, however, is not only cultural or psychological, it is biological. Beneath the fear of imagined monsters lies the reality of actual life forms, stranger than anything we once dreamed. For every myth of a kraken, there exists a real creature adapted to pressure, darkness, and cold in ways we never expected. They are not monsters in the mythical sense, but they are astonishing, and they remind us that the deep sea doesn't need our imagination to be extraordinary. It already is. Which is why the next step in our journey is to look at the life that does exist there, the strange creatures that rewrite biology and show us that mystery doesn't always require myth. Fear has long filled the abyss with imagined monsters, but the truth is that the real creatures of the deep are every bit as astonishing as legend, just in ways we could never have guessed. The darkness, the pressure, and the cold have forced life to evolve strategies so different from what we see on land, or in shallow seas, that encountering them feels like stepping into another world. For scientists, each discovery rewrites assumptions about biology. For the rest of us, these creatures reveal that imagination alone cannot match the creativity of evolution. Consider first the simple fact that life exists at all under such crushing conditions, at depths where pressure is hundreds of times greater than at the surface. Proteins inside cells should collapse, membranes should stiffen, and DNA itself should struggle to function. Yet microbes thrive there, metabolizing slowly but steadily. They've adapted their enzymes to remain flexible even under immense pressure. Their cell structures reinforced to withstand crushing forces. Some rely on chemicals like methane or sulfur to fuel their survival, living entirely separate from the sunlight-based cycles that dominate the surface world. The existence of such organisms challenges one of the most basic ideas in biology, that energy from the sun is the foundation of all ecosystems. In the abyss, life shows that it can build itself on entirely different rules. As you move up from microbes to larger animals, the strangeness deepens. Many fish in the abyss have gelatinous bodies with few rigid structures. Bones and air-filled swim bladders would be liabilities under pressure, so these animals are built like living jelly, their buoyancy controlled by oils or other dense fluids. The result is creatures that look soft, ghostly and fragile, but in truth are perfectly adapted to their environment. They may appear strange to us, but they are efficient solutions to challenges that we can hardly imagine enduring. Take the anglerfish, one of the most iconic deep-sea creatures. Its body is dark and misshapen, its mouth filled with jagged teeth, and from its head extends a lure tipped with bioluminescent bacteria. In the blackness of the abyss, that glowing lure mimics prey, drawing other fish close enough to be snapped up. It's a strategy as brilliant as it is eerie, showing how evolution turns the absence of sunlight into an opportunity. Even stranger is the reproductive strategy of some anglerfish species. Males are tiny compared to females, and when they find a mate, they bite into her body and fuse, eventually becoming little more than a pair of testes supplying sperm. It's a bizarre arrangement, but in a world where encounters between individuals are rare, it ensures reproduction. No myth ever conceived of such a system, yet nature created it because the deep demanded it. Another marvel is the gulper eel, with its enormous mouth capable of swallowing prey much larger than itself. In an environment where meals are scarce, being able to eat whatever you can find, no matter the size, is a survival strategy. Its body is long and whip-like, its tail ending in a bioluminescent organ that glows to attract curious prey. In the dark, the gulper eel becomes a living trap, combining patience with adaptability. It looks unreal in photographs and videos, like a creature sketched by someone imagining aliens. But it is entirely earthly, born of pressures and darkness we struggle to comprehend. Then there are the giant isopods, relatives of the pillbugs you might see on land, but scaled up to the size of dinner plates. Their armoured bodies scuttle across the seafloor, scavenging whatever organic material they find. Like their shallow cousins, they curl up when threatened, but their sheer size is startling. Scientists think deep-sea gigantism, the tendency for some species to grow much larger in the abyss, may result from the cold, which slows metabolism and allows long lifespans, or from the lack of predators that would otherwise limit size. Whatever the cause, the result is creatures that challenge our sense of proportion, as though the deep sea exists in a different scale of reality. Even familiar animals become strange in the abyss. Squids, for example, range from tiny to colossal, with some species stretching longer than buses. For centuries, the giant squid was the stuff of myth, a kraken imagined by sailors. Today, we know it is real. Rare footage has captured its enormous tentacles and dinner plate-sized eyes, organs adapted to capture the faintest glimmers of bioluminescence in the dark. It hunts silently, a true giant living in the shadows, and beyond the giant squid lies the colossal squid, heavier, armed with swivelling hooks on its tentacles, a predator so elusive that only fragments and rare specimens have ever been studied. These animals show that the myths of enormous creatures were not entirely wrong. The ocean does contain giants, just not exactly as legend described them. Bioluminescence itself is one of the most remarkable biological phenomena in the deep. More than 90% of deep-sea species are thought to produce light. They do it through chemical reactions inside their bodies, often using symbiotic bacteria. The purposes vary, attracting mates, luring prey, startling predators, or even camouflaging against faint light from above. Some fish produce counter-illumination, glowing on their undersides to match the dim light filtering down, erasing their silhouettes from predators below. Others flash in patterns like living Morse code, communicating silently in the dark. To us it looks like fireworks drifting through water. To them, it's language and survival. In a world without sunlight, life has invented its own stars. One of the most surprising discoveries of the last half-century has been the ecosystems around hydrothermal vents. Before these were found in the late 1970s, scientists assumed all ecosystems depended ultimately on sunlight. The vents proved otherwise. Spewing mineral-rich, superheated water into the abyss, they create chemical gradients that microbes exploit. Around those microbes, entire food chains flourish. Giant tube worms with red plumes, clams the size of footballs, shrimp with light-sensitive patches on their backs. These creatures thrive in what seems like poison to us, in temperatures that swing between freezing and scalding, in waters laced with sulfur and metals. They rewrite our understanding of biology, showing that life can flourish, not just without sunlight, but in conditions that seem utterly hostile. That discovery has even influenced how we think about life beyond Earth. If ecosystems can thrive in the deep sea without sunlight, then perhaps icy moons like Europa or Enceladus, with oceans beneath their frozen crusts, might also harbour life. Beyond vents, cold seeps provide another example. These are places where methane and other hydrocarbons leak from the seafloor, supporting communities of mussels, worms and bacteria. Like vent ecosystems, they depend on chemosynthesis rather than photosynthesis. And like vents, they reveal that life doesn't just tolerate extreme conditions, it exploits them. Every discovery of such ecosystems adds to the sense that biology is more adaptable, more inventive than we once believed. Not all deep-sea creatures are large or dramatic. Many are small, transparent or delicate, drifting in the water column in shapes so strange they defy easy description. Comb jellies ripple with rows of cilia that scatter light into rainbows. Siphonophores form colonies of specialized individuals linked into a single drifting organism, some stretching longer than whales. These delicate, gelatinous beings may not resemble monsters, but they embody the deep strangeness. They are fragile, yet perfectly suited to a world without light or solid surfaces. To study them is to realize that life can take forms far beyond what we expect from our land-based perspective. For every discovery, countless questions remain. How many species exist in the abyss? How do they interact? What strategies have we not yet imagined? Each expedition that descends into the deep returns with images of creatures never seen before. Sometimes dozens of new species are described from a single dive, and that's with less than 5% of the ocean explored. The implication is staggering. Entire categories of life may exist that we have not yet encountered. Our textbooks are incomplete, our definitions provisional. The deep sea is not just unknown territory, it is unknown biology. The adaptations of these creatures also hold potential for humans. Enzymes that function under pressure and cold could be used in industry. Bioluminescent proteins already power advances in medical imaging and biotechnology. Chemical compounds from vent organisms may inspire new medicines. Each strange adaptation is a reminder that nature is an innovator, and the abyss is its largest laboratory. The challenge is reaching those discoveries without destroying the ecosystems that produce them. Exploration is slow, but exploitation could be fast, and the balance between curiosity and caution will determine how much we learn before it's too late. What's clear is that the abyss is not barren. For centuries, people assumed nothing could live in the crushing depths. Now we know it is teeming with life, much of it unlike anything on the surface. Strange, fragile, glowing, enormous or microscopic, these creatures rewrite biology with every dive. They are not monsters in the mythical sense, but they are every bit as extraordinary. They remind us that the universe is creative, that life finds ways to exist in conditions we once thought impossible. And as astonishing as these creatures are, they are only one piece of the story. Beyond the living organisms, the deep ocean holds phenomena just as fascinating, processes that shape the planet itself. One of the most remarkable is the way the abyss glows not with sunlight but with its own lights, the lanterns of bioluminescence that we have only just begun to understand. Life in the abyss proves that survival is possible even in the most extreme conditions. But survival there doesn't just mean hiding from predators, or scavenging what little food drifts down from above. It also means finding ways to communicate, to attract, to deceive, and to survive in a world without sunlight. That is where one of the most remarkable phenomena of the ocean comes into focus: bioluminescence. The ability of living organisms to create their own light. It is one of the most widespread traits in the deep, and one of the most beautiful. If you think of the darkness of the ocean as an infinite night sky, then bioluminescence is its stars, scattered across the black water, blinking, flashing, and glowing in patterns that are as diverse as the creatures that create them. The chemistry behind it is deceptively simple. Bioluminescence is the result of a chemical reaction inside cells, often involving a molecule called luciferin and an enzyme called luciferase. When oxygen interacts with luciferin, light is released. Different species tweak this basic process with variations, producing colours that range from blue to green, and sometimes red. Blue and green dominate because they travel farthest in water, scattering less than other wavelengths. Red light, so common at the surface, is quickly absorbed in shallow depths and becomes invisible in the abyss. That means red bioluminescence is a kind of secret code, visible only to those who can detect it. What makes bioluminescence remarkable is not just the chemistry, but the diversity of its uses. In the deep, where light from the sun never reaches, making your own light opens a world of possibilities. Some creatures use it as camouflage. It may sound strange, but in the deep sea, glowing can make you less visible. Certain fish produce light on their undersides, matching the faint glow of any light filtering from above. To predators looking up, these glowing bellies erase the animals' silhouettes, blending them into the faint background. Scientists call this counter-illumination, and it's a perfect example of evolution turning absence into opportunity. Other creatures use bioluminescence to hunt. Anglerfish dangle glowing lures to attract prey. A trap that works because curiosity is as strong a force in the abyss as hunger. Dragonfish have bioluminescent bars near their mouths, flashing them as they approach unsuspecting prey. The gulper eel glows with a light at the tip of its tail, drawing fish into range of its enormous mouth. In each case, light becomes bait, an irresistible signal in a world where any brightness is unusual and worth investigating. Defense is another major use. When threatened, some squid and shrimp release clouds of glowing fluid, dazzling predators and giving themselves time to escape. Others produce sudden flashes to startle attackers, like a camera flash in the dark. Some fish even detach glowing organs that drift away like decoys, tricking predators into chasing the wrong target. In the abyss, light can mean life or death, not because it illuminates the environment, but because it manipulates it. Communication is perhaps the most sophisticated role of bioluminescence. Some species flash patterns to signal mates, much like fireflies on land. Others use it to coordinate movements in schools or swarms. For organisms drifting far apart in the vastness of the ocean, light offers a way to say, "I am here." It's a language written in pulses and glows, invisible to us until we bring cameras that can record it. We're only beginning to decipher these codes, but it's clear that bioluminescence is not just a trick of survival, it is an entire system of interaction, as complex as the songs of birds or the colours of flowers. To humans, bioluminescence has always seemed magical. Sailors described seas glowing with waves of light, a phenomenon caused by plankton releasing luminescence when disturbed. These milky seas can stretch for kilometres, turning the surface into a glowing plain visible even from satellites. For those who encountered them centuries ago, they must have seemed like signs or omens, proof that the ocean was alive with mystery. Today, we understand the science, but the wonder remains. Seeing a wave light up with sparks of blue is still breathtaking, still a reminder that life has found a way to paint even the darkest canvas. Bioluminescence also highlights how much we don't yet know. Many deep-sea species glow, but we often don't know why. What specific signals mean, what purposes each flash serves, or how different species interpret them remains unclear. We can guess based on behaviour, But true understanding requires years of observation in environments that are nearly impossible to study without disrupting them. Each expedition brings back new footage of glowing creatures, and each raises new questions. We are watching conversations we cannot yet translate. The importance of bioluminescence goes beyond curiosity. For scientists, studying how it works has real-world applications. Proteins from glowing organisms have been adapted into tools for medical imaging, allowing researchers to trace cellular processes in real time. The discovery of green fluorescent protein, originally from a jellyfish, revolutionized biology. It proved that adaptations from the abyss can change science on land. Other compounds may one day lead to new technologies in lighting, sensors, or communication. What seems like a curiosity is in fact a library of innovation, waiting to be understood. But beyond utility, there is the sheer fact of beauty. The deep is often portrayed as hostile, a place of fear, darkness, and pressure. Yet bioluminescence reveals it as also a place of art, the flashes of light drifting upward, the glowing organs pulsing in rhythm, the sudden spark of a startled shrimp. These are natural spectacles, performances that have been playing unseen for millions of years. It's humbling to think that while humans gazed at the stars above, entire galaxies of light were drifting below, invisible until technology gave us the chance to see them. Bioluminescence also challenges our sense of what is natural. On land, light is something external, from the sun, from fire, from electricity. In the deep, light is part of the body, a built-in tool. It blurs the line between physics and biology, showing how evolution can weave the fundamental forces of nature into living systems. To glow is to embody light, to carry it inside and use it with precision. It's a reminder that biology is not separate from the universe, but an expression of it, shaped by necessity into forms that astonish us. For explorers, encountering bioluminescence is often the highlight of a dive. Imagine piloting a submersible, turning off the external lights and drifting through the black. At first, there is nothing. Then, as the water stirs, flashes begin to appear. Tiny sparks, drifting chains of light, sudden bursts that flare and fade. It feels like entering a dream, as though the ocean itself has awakened to greet you. Those moments are unforgettable, and they remind scientists and explorers alike why the deep sea is worth studying. It is not just about data or samples, it is about witnessing life in forms that expand our imagination. And yet, for all its wonder, bioluminescence is still only one aspect of the deep. The organisms that glow often gather in places where energy is available. One of the most remarkable of those places are hydrothermal vents, where the Earth itself provides heat and chemicals that sustain thriving ecosystems. If bioluminescence shows us how life adapts to darkness, vents show us how life adapts to Earth's raw power. They're alien landscapes on our own planet, and they may hold the key to understanding life not just here, but beyond. Bioluminescence shows us how life can create its own light in the absence of the sun, but it does not explain how entire ecosystems can thrive without sunlight at all. For centuries, scientists assumed that photosynthesis, the process of capturing energy from sunlight, was the foundation of all life on Earth. Plants, algae, and phytoplankton formed the base of food chains, feeding herbivores, which in turn fed carnivores. Energy flowed from the sun downward into every ecosystem we knew. That assumption seemed unshakable until the late 1970s, when scientists discovered something in the deep Pacific that rewrote biology. At hydrothermal vents, plumes of superheated water gushed from cracks in the seafloor, and around them were thriving communities of life, completely detached from the sun. For the first time, we saw proof that ecosystems could be powered not by photosynthesis, but by chemosynthesis, using energy from chemicals instead of light. Hydrothermal vents form along mid-ocean ridges, where tectonic plates spread apart and magma rises from below. Seawater seeps into cracks in the seafloor, heats up as it contacts magma, and emerges back into the ocean carrying dissolved minerals and chemicals. Some vents release water at temperatures over 350 degrees Celsius, hot enough to melt lead, yet the pressure of the deep keeps the water from boiling. As that scalding, mineral-rich water meets the cold seawater, it creates towering chimneys called black smokers, belching dark plumes of chemicals into the abyss. For a long time, scientists assumed nothing could live in such hostile conditions. But when they sent submersibles to study these vents, they found not a barren wasteland but a thriving metropolis of life. The first sight of a vent community stunned the scientific world. Giant tube worms more than a metre long clustered around the chimneys, their bright red plumes waving in the hot current. Clams the size of footballs lay in dense beds. Shrimp with light-sensitive patches on their backs crawled across the rocks. Fish, crabs, and snails moved among them. Instead of emptiness, there was abundance. Instead of isolation, there was community. And instead of photosynthesis, the foundation was chemosynthesis. Microbes used the chemicals from the vent fluid, hydrogen sulfide, methane, and others, to build organic matter. These microbes formed the base of the food chain, feeding the larger animals, and in some cases living symbiotically inside them. The giant tube worms, for example, have no mouth or digestive system. Instead, they house chemosynthetic bacteria in a special organ, feeding them with chemicals from the vent water and receiving nutrition in return. It is a partnership so complete that the worm's entire survival depends on it. This discovery was more than a curiosity. It was a revolution. It proved that life could exist in places we had never considered, places that seemed utterly hostile. It expanded the definition of habitable environments, not just on Earth, but across the universe. If ecosystems could thrive around vents on the ocean floor, then perhaps similar systems could exist on icy moons like Europa or Enceladus, where subsurface oceans touch hot rock below. Hydrothermal vents became not just a biological discovery, but an astrobiological one, suggesting that life may be far more common than we once believed. The vents themselves are dynamic, ever-changing landscapes. Some last for decades, others collapse within years as chimneys grow, break, and rebuild. The communities around them must adapt quickly, recolonizing new vents as old ones vanish. Larvae of tube worms, clams, and shrimp drift in the currents, ready to settle when they find the right chemical cues. It's a precarious existence, tied to the life cycle of the vent itself. Yet despite the instability, the ecosystems thrive, proving that resilience is as much a part of life as stability. What makes vents even more fascinating is that they are not uniform. Black smokers release dark, mineral-laden plumes. White smokers release cooler, lighter-coloured fluids with different chemical compositions. Alkaline vents, like the famous Lost City field in the Atlantic, produce milky fluids rich in hydrogen and methane at lower temperatures than black smokers. Each type supports different microbial communities and different adaptations. The variety reminds us that even in the most extreme environments, diversity finds a way. There is no single recipe for survival. There are many. Studying these systems is not easy. Vents occur along mid-ocean ridges, often in remote locations thousands of kilometers from shore. Reaching them requires research vessels, submersibles, and specialized equipment to withstand heat and pressure. Sampling must be done carefully, as vent fluids can corrode instruments or destroy sensors. Bringing organisms to the surface often kills them, since they depend on both pressure and chemicals that vanish in ordinary seawater. Scientists have developed pressurized aquariums to keep vent species alive in laboratories, but maintaining the exact balance of heat, chemistry, and pressure is a challenge. Every observation is hard-won, and every discovery is precious. Despite these difficulties, the study of hydrothermal vents has already reshaped our understanding of Earth. Geologically, vents reveal how the planet's interior interacts with the ocean, releasing heat and chemicals that influence global cycles. Biologically, they show that life can emerge from chemical energy, suggesting possible pathways for the origin of life itself. Some scientists hypothesize that life on Earth may have begun at vents, where the right combination of chemistry, energy and structure existed billions of years ago. If true, then the deep ocean is not just a frontier, it is the cradle of all biology. Hydrothermal vents also highlight the fragility of deep-sea ecosystems. Because they depend on specific chemical conditions, they are vulnerable to disturbance. Mining for minerals on the seafloor, particularly for metals concentrated around vents, poses a serious risk. Destroying vent fields could wipe out unique species before we even know they exist. The same applies to climate change. Altered ocean chemistry and circulation could impact the formation and stability of vents. Exploration must therefore balance curiosity with caution, ensuring that the drive to study or extract resources does not erase what makes these places extraordinary. From a human perspective, hydrothermal vents are perhaps the closest thing to alien worlds we can visit without leaving Earth. Their landscapes of towering chimneys, glowing plumes and strange creatures are as foreign as any we can imagine on distant planets. To descend into that environment is to step outside the familiar and into a realm that feels designed to challenge assumptions. It's not surprising that many who study vents describe them with awe, as though they are privileged to glimpse a world hidden from ordinary experience. Yet as alien as they seem, vents are deeply connected to our planet. They recycle chemicals, influence ocean chemistry and host life that demonstrates the resilience of evolution. They are reminders that the Earth is not uniform, that its surface is only part of its story. Beneath, in the dark and the heat, lies a world as rich and dynamic as the one we know, and that world is still only partly explored. We've found vents on ridges across the globe, but many remain undiscovered. Each expedition has the potential to reveal entirely new ecosystems, new species, and new chemistry. The story of vents is only beginning. As we reflect on what vents teach us, another aspect of the deep becomes clear. In the absence of light, ecosystems depend on alternatives, whether bioluminescence or chemosynthesis. But when it comes to exploration, we too must find alternatives. We cannot use sight as we do on land or in space. Instead, we rely on sound, sending echoes into the abyss to map what our eyes cannot see. Sonar has become the substitute for vision, the way we sketch the outlines of the deep. If vents are alien worlds, sonar is the tool that lets us navigate among them. It is our ears where our eyes fail, and it has become the foundation of how we know the ocean's shape. Hydrothermal vents show us that life can thrive in places where sight is useless and sunlight never arrives. For the creatures that live there, survival depends on senses other than vision. For us, exploring the deep requires a similar shift. On land and in space, sight is our primary way of knowing. Telescopes gather light from galaxies, satellites photograph entire continents, and even our own eyes can stretch across vast distances when the air is clear. But water changes the rules. Light scatters quickly, absorbed within a few hundred meters. By the time you reach the deep sea, sight is gone. To understand what lies below, we rely not on eyes but on echoes. Sound becomes our substitute for vision, sonar our way of sketching the unseen world. Sound travels differently in water than in air. In fact, it travels faster, more than 4 times as fast, and it carries farther. A low-frequency sound wave can travel hundreds, even thousands of kilometers in the ocean, bending with temperature and pressure in ways that create channels through which it can pass with minimal loss. Creatures of the sea have known this far longer than we have. Whales communicate across vast distances with low-frequency calls. Dolphins navigate and hunt using echolocation, bouncing high-frequency clicks off prey and obstacles. Humans, latecomers to the ocean, borrowed the same principle and turned it into sonar, sound navigation and ranging. The idea is simple in concept but profound in application. A pulse of sound is sent into the water. It strikes an object, the seafloor, a school of fish, a submersible, and returns as an echo. By measuring the time it takes to return and the strength of the signal, we can infer distance, shape, and sometimes even texture. With sonar, the invisible becomes visible, at least in outline. Ships have used it for navigation, fishermen for locating schools, militaries for detecting submarines, and scientists for mapping the ocean floor. Without sonar, most of what we know about the shape of the deep ocean would not exist. Sonar mapping works in layers. At its most basic, single-beam sonar sends sound directly downward from a ship and records the echo. This gives depth at a single point, like shining a flashlight straight down. Move the ship and you build a line of measurement slowly tracing the contour of the seafloor. More advanced is multi-beam sonar, which sends out a fan of sound waves, covering a swath of the seafloor at once. By moving in systematic patterns, ships can map wide areas in 3 dimensions, building detailed images of ridges, trenches, and plains. The data collected this way has revealed mountains taller than Everest hidden beneath the waves, canyons deeper than the Grand Canyon, and vast plains stretching farther than deserts. Still, sonar is not sight. It doesn't reveal colour or fine detail. It creates outlines, geometric sketches, shadow-like images. For scientists, these sketches are invaluable, but they are not the same as photographs. They give us the shape of the unknown, but not its face. That's why even with modern sonar, the ocean floor remains partly a mystery. We can see its contours, but not the life or textures that cover them. To see those, we must still send cameras and submersibles. Sonar tells us where to look, not what we'll find. The limitations of sonar are as important as its strengths. High-frequency sound provides more detail but fades quickly, useful only at short ranges. Low-frequency sound travels farther but gives blurrier images. Ships must spend weeks crisscrossing the same area to build accurate maps, and even then, coverage is patchy. Only a fraction of the seafloor has been mapped in high resolution. Most of the ocean is represented by low-resolution data, enough to show broad features, but not the fine structures where ecosystems may hide. To map the ocean in the same detail as the Moon or Mars would require centuries at the current pace. Sound also carries complications. Marine animals rely on it too, and human use of sonar can interfere with their communication and navigation. Whales, in particular, are sensitive to certain frequencies. Loud sonar pulses have been linked to strandings, disorienting whales and dolphins. This raises ethical questions about how we balance exploration with the health of ecosystems. Sound may be our eyes in the deep, but we must use it carefully, remembering that we are not the only ones who depend on it. Despite these challenges, sonar has transformed our understanding. Before its invention, maps of the seafloor were filled with guesswork, often nothing more than vague estimates. Today, sonar has revealed mid-ocean ridges stretching around the globe like seams on a baseball. It has uncovered seamounts rising thousands of meters, some harbouring ecosystems we never suspected. It has shown us trenches that plunge into the crust, places where tectonic plates collide and recycle the Earth itself. These revelations are not small. They reshape geology, oceanography, and biology alike. They remind us that the Earth is not fully known, even in its largest features. Beyond mapping, sonar helps us study life. Schools of fish scatter sound differently than water, allowing scientists to estimate biomass. Jellyfish, squid, and even plankton leave signatures in sonar readings. By calibrating these signals, researchers can track migrations, feeding events, and ecosystem dynamics. It's a way of seeing the invisible, turning echoes into knowledge. For creatures too fragile to capture or too elusive to observe directly, sonar provides indirect evidence of their existence and behaviour. Submarines and ROVs also rely on sonar for navigation. In the absence of GPS beneath the waves, sonar provides orientation. It guides vehicles through canyons, helps them avoid obstacles, and lets them position themselves relative to the sea floor. Without it, piloting in the dark would be like flying blind. With it, operators can build mental maps, stitch together images, and plan missions with confidence. It's not perfect, but it's the closest thing to sight in a world where sight doesn't work. The role of sound in exploration also highlights a contrast. On land and in space, light is the medium of knowledge. In the ocean, it is sound. This inversion challenges our assumptions. We think of seeing as knowing, but in the deep, hearing becomes knowing. Maps are not drawn by cameras but by echoes. Discoveries are not always visible but audible. To explore the ocean is to enter a world where our primary sense is reversed, where we must rely on ears instead of eyes. That shift is part of what makes the deep feel so alien. It is not just a different place. It is a place that demands different ways of knowing. And yet, even with sonar, we are far from complete understanding. The technology reveals shapes and outlines but leaves mysteries unsolved. What lives in the shadows of those ridges? What ecosystems thrive on the slopes of those seamounts? What processes shape the sediments of those plains? Sonar points us toward questions, but it cannot answer them. It is a guide, not a revelation. For all its power, it reminds us that the ocean still resists full comprehension. This reliance on sound also underscores an irony. We know more about the surface of distant planets than the floor of our own ocean. Satellites have mapped Mars in exquisite detail, while vast stretches of Earth's seafloor remain roughly sketched. That comparison leads to a natural question. Why is it that space, so distant and hostile, is better mapped than the ocean, which lies beneath our feet? The answer lies partly in physics, partly in funding, and partly in culture. Which leads us to consider the strange reality that we know Mars better than Mariana, and space better than the sea. Sonar lets us map the ocean with echoes, but even with that advantage, the truth is hard to ignore. We know more about the surface of Mars than we do about the deepest trenches of our own planet. It sounds impossible at first. Mars is tens of millions of kilometers away, a cold desert wrapped in thin atmosphere. The Mariana Trench lies just a few hundred kilometers offshore, within reach of ships and machines. And yet the comparison is real. We have detailed topographic maps of Mars, high-resolution images of its craters and valleys, and even rovers rolling across its surface. In contrast, much of the Mariana Trench remains little more than a shaded outline on our charts. The question is why? Why does a world so far away feel more familiar than one beneath our own oceans? The reasons begin with physics. Light travels easily through the vacuum of space, allowing satellites and telescopes to capture sharp images of planets, moons, and asteroids. Radio waves pass through space as well, carrying data from distant probes back to Earth with clarity. In contrast, water absorbs and scatters light, blocks radio waves, and distorts signals. Cameras work only at close range in the deep. Communication requires tethers or slow acoustic methods. Every observation of the ocean is limited, partial, and difficult. By comparison, space is vast but transparent. Instruments can see across millions of kilometers with relative ease, while the seafloor just a few kilometers down remains hidden. Technology has followed these physical rules. Space probes can orbit planets indefinitely, taking photographs for years. Satellites can map surfaces globally with consistency. Rovers can send back images and measurements daily. In the ocean, submersibles last only hours at depth before they must surface. ROVs are tethered, limited by cables. AUVs run out of battery after a few days. The endurance gap is enormous. Space machines operate like surveyors, tirelessly building complete data sets. Ocean machines operate like scouts, dipping briefly into the unknown before retreating. It's not that the ocean is farther, it's that the conditions make persistence much harder. But physics and technology are only part of the story. The rest comes down to priorities. Since the mid-20th century, space exploration has been a symbol of progress, competition, and ambition. The space race of the 1960s turned the moon into a geopolitical prize, and decades later, Mars has become the next frontier. Billions of dollars have flowed into agencies like NASA and ESA, funding rockets, satellites and probes. Each mission is celebrated, televised and commemorated. Public imagination is stirred by visions of astronauts walking on other worlds, of colonies, of humanity reaching beyond Earth. That cultural weight fuels funding, which fuels technology, which fuels discoveries, creating a feedback loop that accelerates space research. Ocean exploration, in contrast, has not enjoyed the same spotlight. There was no ocean race to match the space race. Few politicians campaign on mapping trenches or funding hydrothermal research. The discoveries, while extraordinary, rarely make headlines. A new species of worm or a clearer map of a ridge doesn't inspire the same drama as a rocket launch. The result is a slower pace, fewer missions and less investment. Where space has become a theatre of human aspiration, the ocean remains in the public eye, a place of quiet curiosity. Important, but not urgent. Fascinating, but not iconic. Funding decisions reflect this disparity. NASA's annual budget has often exceeded billions of dollars, supporting missions across the solar system. In contrast, the agencies dedicated to ocean research operate on far smaller scales. The National Oceanic and Atmospheric Administration in the United States, for instance, receives only a fraction of NASA's funding, and only a fraction of that goes to deep-sea exploration. The imbalance is striking, and it explains why satellites have mapped Mars to a resolution of meters, while most of Earth's seafloor is mapped only in kilometers. There is also an irony in perception. Space is often described as the final frontier, a phrase that implies Earth is already known. But the truth is that Earth still holds frontiers as vast as any beyond it. The deep ocean is one of them. To say we know Mars better than Mariana is not to diminish space exploration, but to highlight how much of our own planet remains mysterious. We look outward and dream, while downward lies a frontier we have barely touched. Part of the fascination with space comes from its sense of destiny. Space suggests expansion, the possibility of migration, the dream of survival beyond Earth. It feels tied to humanity's future. The ocean, while vital, doesn't offer the same narrative of escape. It is not seen as a place to colonize or build civilizations, but as a place to study and preserve. That makes it harder to rally large investments, even though its role in regulating climate, supporting biodiversity, and shaping Earth's systems is every bit as important. The lack of urgency keeps funding modest, and modest funding keeps progress slow. Yet when you compare the two frontiers, the irony deepens. Space is distant and barren, with no life that we have yet found. The ocean is close and teeming, holding ecosystems as strange and wondrous as anything we could imagine on another planet. In terms of science, exploring the ocean offers immediate rewards, from new species to new medicines to insights about Earth itself. And yet the romance of space continues to outshine the reality of the sea. Perhaps it is because humans are always drawn to horizons. The stars are visible every night, calling us outward. The ocean hides its mysteries beneath a flat surface, offering no glimpse of what lies below. One invites dreams, the other conceals them. The comparison between space and sea also reflects differences in accessibility. Anyone can look up and see the stars, inspiring a universal sense of wonder. Few can look down into the deep ocean. Its mysteries remain invisible, requiring ships, machines, and expertise to witness. That invisibility makes it harder to capture collective imagination. Space belongs to everyone, at least in vision. The ocean, paradoxically, feels distant even though it surrounds us. Still, progress in ocean exploration continues, and comparisons with space may help rather than hinder. By pointing out that we know Mars better than Mariana, scientists emphasize the need for balance. It is not a choice between one or the other. Both are valuable, both expand knowledge, both shape our understanding of life. But if space inspires us to look outward, perhaps the ocean should inspire us to look inward, to realise that frontiers exist beneath as well as above. The ocean is not simply a barrier or a resource, it is a realm of discovery as worthy of attention as the stars. Some efforts aim to bridge this gap. International projects are working to map the entire seafloor in high resolution by the coming decades. Advances in autonomous vehicles promise longer missions at lower cost. Partnerships between nations, universities and private groups are growing. These efforts may not match the scale of space exploration yet, but they reflect a recognition that Earth's last frontier deserves more than passing interest. The hope is that as awareness grows, so too will investment, and the ocean will begin to receive the kind of systematic attention that space already enjoys. When we place space and sea side by side, we see more than differences in technology or funding. We see differences in how humanity defines its priorities, its dreams and its fears. Space has become a canvas for imagination. The ocean has remained a mirror of reality. Yet both hold mysteries, and both hold lessons. One teaches us about the universe beyond Earth. The other teaches us about the foundation of life on Earth itself. Ignoring either would be a mistake, and while comparisons help clarify the gap, the truth is that the ocean matters not only for curiosity but for survival. Its depths store heat, absorb carbon, and regulate climate in ways that affect every breath of air and every drop of rain. The deep holds secrets not just of biology, but of Earth's future. If we neglect it, we risk ignorance at a time when knowledge is essential. The sea is not simply a mystery. It is a key to our survival, which brings us to another reason why exploring it matters. Beyond myths, beyond monsters, beyond comparisons with space, the deep ocean hides truths about climate, about history, and about the changes shaping our planet, and in those truths lies the question of our future. We often think of the deep sea as separate from our daily lives, a place so far below the surface that it has little to do with the air we breathe or the weather we feel. Yet the truth is that the deep ocean is not just a passive background. It is an active system, influencing climate, storing secrets of Earth's past and quietly shaping our future. If space exploration tells us where we might go, the ocean tells us whether we can stay. And the more we learn, the clearer it becomes that understanding the deep sea is not a luxury. It is a necessity. The ocean is Earth's largest climate regulator. It absorbs heat from the atmosphere, stores carbon dioxide, and redistributes energy through currents that flow across the globe. The surface waters interact with winds and weather, but the deep acts as a reservoir, absorbing changes slowly and releasing them just as slowly. This inertia gives the climate system stability, but it also hides long-term shifts. What happens in the abyss does not stay there. It returns to the surface in decades or centuries, shaping weather, ecosystems, and even civilizations. One of the most important processes in this system is the global conveyor belt, the thermohaline circulation. Warm surface waters flow poleward, cool, sink, and return along the depths, carrying heat and nutrients around the planet. This circulation ties the Atlantic, Pacific, Indian and Southern Oceans into a single system, one that redistributes energy and sustains life. It is a planetary heartbeat, pulsing on timescales far longer than human lives, and yet, like any heartbeat, it can falter. Climate change is altering the balance of temperature and salinity that drives it. Melting ice, shifting winds, and warming waters are changing the density gradients that power the currents. If the conveyor slows or stalls, the consequences could be profound. Shifting rainfall patterns, altering monsoons, raising sea levels unevenly, and disrupting ecosystems on land and in the sea. The deep sea also acts as a carbon sink. When plankton at the surface die, their remains sink, carrying carbon with them. Some are consumed on the way down, but some reach the depths, where they may be buried in sediments for millennia. This biological pump helps regulate atmospheric carbon dioxide, moderating climate. Without it, levels of greenhouse gases would be far higher and the planet far warmer. Yet this system is delicate. Changes in ocean chemistry, temperature and circulation can alter how much carbon sinks, how much is stored, and how much returns. The abyss is not a static vault. It is an active player, and as we alter the surface, we alter the depths. Sediments at the bottom of the ocean are not just passive layers of mud. They're archives. Layer by layer, year by year, they record the history of Earth's climate. Tiny shells of plankton, chemical signatures and mineral deposits preserve information about temperature, carbon dioxide levels, and circulation patterns stretching back millions of years. By drilling cores into these sediments, scientists reconstruct the story of ice ages, warm periods, and abrupt climate shifts. The deep sea holds the memory of Earth's climate, a record we cannot find anywhere else. Reading it helps us understand not just the present but the future, because it shows how the planet responds to change. It reveals thresholds, tipping points, and rhythms. It reminds us that climate is not stable, and that our current trajectory is not without precedent, but also not without danger. Hydrothermal vents and other geologic features in the deep also influence global cycles. The chemicals they release feed microbial communities, which in turn affect carbon and nutrient cycles. The minerals carried by vents spread into the ocean, altering chemistry on scales we are only beginning to understand. These processes are subtle, hidden, and slow, but they matter. The Earth's interior and its oceans are not separate. They are linked, and that link runs through the deep. Climate change is making the need to understand these processes urgent. The ocean has absorbed more than 90% of the excess heat from global warming, much of it stored in the upper layers, but some reaching the abyss. This hidden heat shapes the pace of melting ice, the strength of storms, and the resilience of ecosystems. Without accurate data on how the deep stores and redistributes heat, our models of future climate are incomplete. It is like trying to predict the future of a patient without knowing what is happening in their heart and lungs. The surface tells part of the story, but the depths carry the rest. Acidification is another silent change. As the ocean absorbs carbon dioxide, its chemistry shifts, lowering pH and affecting organisms that build shells or skeletons from calcium carbonate. Most attention has focused on coral reefs near the surface, but the deep is vulnerable too. Cold waters absorb more carbon dioxide, meaning the abyss may experience greater changes. Deep-sea corals, which grow slowly over centuries, are at risk. Their decline would ripple through ecosystems, removing habitats for countless species. Acidification in the deep is harder to see, harder to measure, but no less important. The deep also hides more immediate secrets. Lost shipwrecks, buried under sediment, hold clues to human history. Cables and infrastructure laid across the seafloor carry data that shapes our daily lives, vulnerable to hazards we barely monitor. Potential reserves of minerals and resources lie in nodules and crusts, tempting industries to begin mining, yet raising questions about environmental impacts. Each of these hidden aspects reminds us that the abyss is not irrelevant. It is a place where natural processes and human activities meet, often in ways we do not yet understand. Even life itself in the deep may hold keys to the future. Microbes adapted to extreme pressure and chemistry may yield enzymes useful in medicine or industry. Compounds from vent organisms may inspire new treatments. Adaptations to cold, dark, and pressure may expand biotechnology in ways we cannot yet imagine. Every strange creature in the abyss is a potential library of solutions waiting to be read. But accessing those libraries requires exploration, and exploration requires investment. If we ignore the deep, we ignore possibilities that could shape the future of science and health. The challenge is that the deep is slow, and human society is impatient. Climate shifts in the abyss unfold over decades or centuries, while political and economic decisions turn on years. The mismatch of timescales makes it easy to ignore the deep. Its changes are real but hidden, important but subtle. Yet that is precisely why it matters. By the time its signals reach the surface in obvious ways, the processes driving them may already be locked in. To anticipate the future, we must listen to the whispers of the abyss before they become shouts. Exploration of the deep is not just about curiosity, it is about preparation. It is about knowing how much heat the ocean can absorb before currents change, how much carbon it can store before chemistry shifts, how ecosystems respond to pressure before collapse. The mysteries of the abyss are not just academic. They are practical, tied directly to agriculture, fisheries, weather and survival. Every layer of sediment, every measurement of current, every sample of water tells us something about the road ahead. And yet, despite all this, the deep remains underexplored. We spend billions on satellites that monitor the atmosphere in real time, but only modest sums on the systems that monitor the abyss. We dream of colonizing Mars, but we hesitate to fully understand the foundation of the planet we already inhabit. The irony is striking. The future of humanity may depend less on the red deserts of another planet than on the black waters beneath our own. To face climate change, we must face the ocean. To prepare for the future, we must understand its depths. It is not optional. It is essential. The secrets of the abyss are not just curiosities. They are warnings, guides, and opportunities. They show us where we have been, where we are, and where we might go. Ignoring them is like sailing blind into a storm. But climate is not the only secret hidden in the deep. Alongside the natural archives of sediments and currents lie the remains of human history. Shipwrecks, artifacts, and traces of civilizations lost to time rest quietly beneath the waves. They too are part of the story, reminding us that the ocean is not only a regulator of climate but a keeper of memory. And as we turn to those memories, we find that the deep sea is not only about the planet's future, but also about our past. The deep ocean is not only a vault of natural history storing the records of climate and the processes of the Earth itself, it is also a vault of human history. Beneath its surface lie the remains of countless ships, planes, and even traces of ancient civilizations. They are hidden not because they lack importance, but because they rest in a place that is difficult to reach and harder to study. For as long as humans have sailed, they have left pieces of their story behind on the seafloor, and the ocean has kept those secrets for centuries, sometimes for millennia. To look into the abyss is not only to discover the unknown life and geology of our planet, but also to rediscover pieces of ourselves. Shipwrecks are the most visible examples of this hidden history. From ancient trading vessels to modern warships, from small fishing boats to massive liners, the ocean floor is littered with stories of journeys interrupted. Each wreck is more than a pile of wood, steel, or cargo. It is a snapshot of a moment in time, preserved by depth and darkness. Some wrecks hold treasures, others hold ordinary goods, but all hold information about how people lived, how they travelled, what they valued, and sometimes how they fought. In that sense, the ocean is the world's largest archive of human movement. One of the most famous wrecks to capture public imagination is the Titanic. Resting at more than 3,800 metres, it was long thought unreachable until technology made exploration possible. When images of its broken hull were first broadcast, they revealed not just the scale of the disaster, but the strange preservation that the deep provides. The cold, the lack of light, and the absence of strong currents had kept much of the ship intact, even as rust-eating bacteria slowly consumed the steel. To see it lying in the abyss was to realise that the ocean does not erase history quickly. It keeps it, silently, for those with the tools to look. But the Titanic is only one among thousands. War has left wrecks across the seas, from fleets sunk in battle to submarines lost without trace. Each one is both a grave and a time capsule. Cargo vessels have gone down in storms, carrying goods that now rest undisturbed, revealing ancient trade networks and modern economies alike. Fishing boats, liners, and explorers' ships tell stories of ordinary lives as much as extraordinary ones. Together, they form an underwater museum larger than anything built on land, though one that few will ever see. Beyond ships, the ocean also hides traces of civilizations lost to rising seas. During the last ice age, sea levels were far lower. As the ice melted and the oceans rose, coastlines shifted dramatically, drowning settlements, tools, and landscapes. Archaeologists now know that beneath shallow seas lie entire chapters of human history, from prehistoric camps to early villages. The deep itself may hold even more, though reaching it is far harder. What has been discovered suggests that the ocean floor is not just a graveyard of ships, but also of places where people once lived. One striking example is Doggerland, a landmass that once connected Britain to mainland Europe. 10,000 years ago, it was a rich landscape of rivers, lakes, and forests. As sea levels rose, it was submerged, leaving only fragments of tools and bones dredged up by trawlers as evidence of its existence. Other submerged landscapes lie scattered around the world, from the coasts of India to the Black Sea. Each one represents not just geology, but memory, places where people hunted, farmed, and told stories before the waves covered them. The deep holds not only nature's records, but our own. Airplanes too lie in the abyss, from wartime bombers to commercial jets. They rest alongside ships, forming newer layers of human presence. The search for lost planes often captures public attention because it is tied to recent memory. But the difficulty of finding them reminds us again of how vast and hidden the ocean is. A plane that vanishes into the sea may never be found, swallowed not by malice but by scale. Even with sonar, even with satellites, the abyss keeps secrets well. What makes the deep such a powerful archive is the way it preserves. On land, ruins are eroded by wind, rain, and plants. In shallow seas, waves and currents break down wood and stone. But in the depths, cold and darkness slow decay. Objects rest undisturbed for centuries. Metals corrode, yes, and bacteria consume, but slowly, often leaving recognizable shapes long after they would have vanished elsewhere. In that sense, the abyss is both a destroyer and a preserver, erasing some details while keeping others far longer than the surface ever could. For archaeologists and historians, exploring these wrecks and ruins offers more than curiosity. It provides data about trade, technology, and culture. Ancient amphorae on a seafloor reveal what people carried and where they sailed. Weapons and armour tell of battles fought. Everyday objects, tools, pottery, coins, remind us of ordinary lives. Each discovery is a bridge to the past, built not in museums but on the ocean floor, and each one deepens our sense that human history is intertwined with the sea, shaped by it and stored within it. There is also a human element that goes beyond science. Many wrecks are graves, places where lives ended suddenly. To explore them is to touch not only history but memory. The Titanic is a symbol partly because it carries that weight. Thousands of lives lost, stories unfinished, dreams cut short. Warships hold similar weight, resting places for those who never returned. Exploration of these sites must balance curiosity with respect, remembering that beneath the fascination lies tragedy. The Oceans Archive is not only scientific, it is also emotional. Modern technology is making it easier to find and study wrecks. Sonar reveals shapes on the seafloor. ROVs can film details without disturbing them. AUVs can map wide areas in search of anomalies. With each advance, more of the hidden record becomes accessible. Yet most wrecks remain undiscovered, not because they are lost forever, but because the ocean is so vast. Every new discovery reminds us how incomplete our knowledge still is. These wrecks and submerged sites also connect with larger themes. They remind us that sea level is not fixed, that coastlines change, that what seems permanent can vanish. They show us that human history is fragile, easily hidden, easily forgotten. They highlight how dependent we are on the ocean for travel, trade, and survival. and how much risk that dependence carries. They show that the abyss is not separate from us, but deeply tied to our story. And like everything in the deep, they carry mysteries. How many ancient settlements lie undiscovered? How many wrecks still hold secrets of technologies, cargoes, or stories? How much of human history is missing simply because it is hidden beneath waves? These questions drive exploration as much as biology or geology. To know ourselves fully, we must look not only at land, but at sea. Still, even as the ocean holds our past, it also holds our present. Wrecks become artificial reefs, colonized by corals, fish, and invertebrates. Planes and ships become ecosystems, transformed from machines of travel or war into havens of life. This blending of human and natural history is unique to the ocean. On land, ruins decay slowly, but rarely do they become habitats. In the sea, they do. The ocean repurposes our past, turning tragedy into new life. It is a reminder that history does not end in the deep. It changes, reshapes, and continues. Yet for all the fascination with wrecks and civilizations, the majority of the deep's ecosystems are not built on human artifacts but on natural structures. Coral gardens, sponge fields, and microbial mats cover vast areas we have yet to study. These unseen ecosystems are as mysterious as any wreck, as vital as any history. They form the living fabric of the deep, sustaining food webs that stretch to the surface. They too are part of the story, and they too are largely unknown. Shipwrecks and traces of lost civilizations remind us that the deep ocean holds fragments of human history. But what dominates the abyss is not our story. It is the story of life itself. For all the fascination with giant squids or glowing fish, the majority of the deep remains invisible not because it is empty, but because it is filled with ecosystems too subtle, too fragile, or too vast for our eyes to catch easily. They are webs of interaction, from microbes we can barely see to giants that drift through the darkness, bound together in food chains that are intricate and resilient. To speak of the deep only in terms of its monsters or wrecks is to miss what makes it truly remarkable. It is a living system, unseen but essential, holding together the ocean's balance and by extension, much of the planet's balance. The foundation of that system begins with microbes. They may be small, but they are everywhere, inhabiting sediments, vent fluids, and the water column itself. In the abyss, microbes do the work that plants do on land or in surface waters. They fix carbon, recycle nutrients, and form the base of the food chain. At hydrothermal vents, they thrive on chemical energy, oxidizing sulfur or methane. In sediments, they break down organic matter that has sunk from above, ensuring that nutrients are not lost but return to circulation. Even in the open water, free-floating microbes transform dissolved chemicals into forms that other organisms can use. Without them, the deep would not be a reservoir of life. It would be a graveyard. These microbes are not uniform. They form diverse communities, each adapted to local conditions. Some withstand extreme heat, others extreme pressure, others both. Some live in symbiosis with larger animals, housed inside tube worms or clams. Others form mats on rocks, creating visible layers of life. Still others drift invisibly, their presence detectable only through chemical traces or genetic sequencing. For scientists, they represent one of the largest reservoirs of biodiversity on Earth, mostly undescribed, mostly unknown. To study them is to realize that we have barely begun to map the complexity of life in the deep. From microbes, the food web rises. Particles of organic matter called marine snow drift downward from the surface. This slow rain of dead plankton, fecal pellets, and organic fragments feeds countless organisms in the water column and on the sea floor. Tiny crustaceans consume it. Fish consume the crustaceans, and larger predators consume the fish. It is a chain built on scarcity, where every particle matters. In some places, carcasses of large animals sink rapidly, creating sudden oases of abundance. A whale fall, for example, can support communities for decades, as scavengers strip the flesh, worms bore into the bones, and microbes consume the lipids within. In a world of scarcity, such events are feasts that reshape ecosystems. The midwater zone between surface and abyss is filled with life that forms part of this unseen system. Lanternfish, perhaps the most abundant vertebrates on Earth, migrate daily from the deep toward the surface, feeding at night and retreating by day. Their movements transport carbon and nutrients vertically, connecting shallow and deep ecosystems. Squid, jellyfish and other creatures join this migration, forming the largest daily movement of biomass on the planet. It happens in silence and darkness, unseen by human eyes, yet it shapes the balance of the ocean. At the sea floor, other webs form. Corals and sponges build slow-growing communities, providing habitats for fish and invertebrates. Crabs, sea cucumbers, and brittle stars scavenge sediments, turning detritus into energy. Predators like grenadiers or rat-tail fish hunt smaller animals, their slow metabolisms suited to an environment where meals are rare. Gigantic worms, deep-sea prawns, and countless other species contribute, each a link in chains that stretch across kilometres. The diversity is staggering, even though much of it is still undescribed. Each expedition reveals new forms, reminding us that we do not yet know the extent of what lives there. Gigantism in the deep adds another layer of fascination. Some species grow to sizes far beyond their shallow water relatives. Giant isopods crawl across the bottom, armoured like enormous pillbugs. Jellyfish with tentacles stretching dozens of metres drift silently. Siphonophores form colonies longer than blue whales, delicate chains of specialised individuals functioning as one. These giants are not myths. They are realities, shaped by cold temperatures, long lifespans, and ecological niches that allow size to flourish. They remind us that scale in the deep is flexible, that life does not obey our expectations but invents its own rules. The giants coexist with the smallest forms, microbes and plankton, in webs that seem improbable yet function smoothly. Energy flows upward and downward, sideways and across, in patterns we barely understand. It is not a simple chain, but a network, with redundancy and flexibility. If one source of food fails, another may fill the gap. If one species declines, others adapt. This resilience is part of why the ocean has endured change for millions of years. But resilience has limits, and human activity is testing them. Climate change, acidification, and pollution are altering the deep in ways we cannot fully track, because we do not yet know enough about its webs. The food web also connects the deep to us directly. Fisheries harvest species that depend on deep processes. Climate regulation depends on microbial activity. Carbon storage depends on sinking particles and the creatures that consume them. Our own survival is tied invisibly but firmly to ecosystems we cannot see. That connection is easy to ignore because it is not obvious. Yet every breath of oxygen, every stable season, every reliable harvest owes something to processes in the abyss. To call them unseen is not to say they are irrelevant. It is to admit that our eyes have not yet caught up with their importance. Studying these systems is difficult because of their scale. Microbes cannot be cultured easily, and their diversity is immense. Giants like siphonophores are too fragile to collect intact. The midwater zone is vast, filled with creatures that avoid nets or disintegrate when captured. New tools are helping, genetic sequencing, deep cameras, in situ experiments, but they only scratch the surface. We're still learning how to ask the right questions, let alone how to answer them. The unseen ecosystems remain unseen not only because they are far away, but because our methods are still crude compared to the complexity they demand. Yet progress is steady. We now know that microbial diversity in the deep may rival that of rainforests. We know that whale falls create unique successions of life. We know that lanternfish and other migrants play roles in carbon cycles larger than many human activities. Each of these discoveries expands the picture. filling in pieces of the puzzle that is far from complete, and each emphasizes that the deep is not a void. It is a web, intricate and dynamic, built of small and large, fragile and strong, hidden but essential. If the ocean hides ecosystems so complex, then it is natural to wonder what else it hides. For centuries, myths of giant squids or sea serpents reflected that wondering. Today science has confirmed some giants, but others may still wait. The abyss is vast and exploration has been limited. It is not unreasonable to imagine that large species remain undiscovered, drifting through the black, eluding our machines. The possibility of the unknown is not fantasy. It is a logical conclusion of how little we have seen, and it is that possibility that keeps curiosity alive, driving us deeper into mystery. Ecosystems of microbes and giants show that the deep ocean is already stranger than most myths ever dare to suggest. Yet curiosity always circles back to a question we cannot quite let go of. What else is out there? If so much life has already been discovered in the small percentage of the ocean we've managed to study, what might still wait in the vast areas we have not touched? The possibility of the unknown is not an abstract idea when it comes to the deep sea. It is a daily reality. Each dive brings back new species. Each net pulls up creatures never catalogued. Each sonar trace reveals features we never mapped. It is natural to wonder whether some of the legends of old, or new marvels beyond imagination, still drift through the abyss unseen. The giant squid is a perfect reminder of how myths can turn into biology. For centuries, sailors spoke of enormous tentacled monsters dragging ships beneath the waves. The stories were exaggerated, filled with terror and spectacle, but at their heart lay something real. Deep in the oceans lived squids of enormous size, reaching lengths of more than 10 meters, with eyes as large as dinner plates and tentacles armed with suction cups lined with sharp rings. For most of human history, they were never seen alive. Only dead specimens washed ashore or were pulled from nets, their bodies battered and their true form uncertain. Scientists argued over whether they were real or mere fantasy. Then, in the early 21st century, the first images of live giant squids in their natural habitat were captured. The myths had a kernel of truth. The monsters existed, though not quite as sailors had imagined. Even larger is the colossal squid, heavier and more robust than its giant relative, with swivelling hooks on its tentacles and eyes, among the largest of any creature on Earth. Few specimens have ever been studied, but what little we know suggests it is a formidable predator living in the Southern Ocean where few humans ever go. Its existence was once doubted as well, until fragments and occasional captures proved otherwise. If animals of such size and power can remain hidden for centuries, then it is reasonable to ask what else might still be out there. The possibility of the unknown does not stop with squids. Some scientists speculate about enormous sharks, distant cousins of known species, living in trenches or remote waters. Megalodon, the extinct giant shark, is sometimes imagined as still lurking in the abyss, though evidence shows it disappeared millions of years ago. Still, the persistence of the idea speaks to the ocean's mystery. When the depths are so unexplored, it feels natural to wonder whether extinction is always certain, or whether some lineages may survive unnoticed in the black. Beyond giants, there may be entire categories of life unfamiliar to us. Most new discoveries so far have been smaller. Fish with transparent heads, worms with metallic scales, jellyfish shaped like parachutes. Yet the diversity suggests that evolution in the abyss has followed countless paths we have yet to glimpse. Every strange adaptation we have found hints at others still waiting. Creatures with forms we have not imagined, strategies we have not predicted, and life cycles we cannot yet explain may drift or crawl somewhere in the darkness. The possibility of encountering them is not fantasy but expectation. With so much of the ocean unexplored, it would be surprising if we had already seen its strangest forms. Even microbial life holds unknowns that could reshape science. genetic surveys of deep waters reveal sequences that do not match any known organisms. They hint at entire groups of microbes still undescribed, metabolisms unrecorded, and biochemistry unlike anything we know. These invisible unknowns may be as revolutionary as any giant squid, offering insights into biology, chemistry, and the origins of life. When we think of discovery, it is easy to picture large animals, but in truth the smallest may hold the most profound secrets. The allure of the unknown also ties into the human imagination. Myths of sea serpents, krakens, and leviathans endure because they symbolize what we do not yet understand. Each time a discovery proves that myths were partly right, interest in the remaining mysteries grows stronger. If giant squids were real, why not other creatures? If vents host entire ecosystems where none were expected, what else lies beyond? The deep sea is a constant reminder that skepticism and wonder are not opposites. They are partners. Science tests myths, but myths often point toward the questions worth asking. The difficulty is proving what might exist. The ocean swallows evidence easily. A carcass sinks quickly, leaving no trace. Vast areas remain unsurveyed. Animals adapted to avoid predators are also adept at avoiding our machines. Even when cameras and sonar search, the ocean scale makes it easy to miss what is rare. That is why so many questions remain open. How many giant squids are there? How do colossal squids live and hunt? Do other large species remain undiscovered? We cannot yet say. The unknown is not a failure of science, it is the reality of scale and limits. There are also creatures that once seemed mythical, but are now routine parts of marine biology. The coelacanth, a fish thought extinct for 65 million years, was rediscovered in the 20th century. Its discovery was a reminder that the ocean can hide survivors, carrying lineages through deep time without our knowledge. Though rare, such rediscoveries show that the boundary between extinct and extant is not always as clear as we assume. The deep is vast enough to hold secrets for millennia. The possibility of the unknown extends beyond animals into landscapes. Entire ecosystems, vent fields, seamount communities, and cold seeps remain undiscovered. Each time we map a new area, we find new habitats, new species, new dynamics. The unknown is not an exception, but the rule. That rule means that speculation about undiscovered giants is not absurd. It is consistent with the scale of what remains hidden. For explorers, this possibility is part of the motivation. Each dive carries the chance of encountering something never seen before. Each net may hold a new species. Each sonar sweep may reveal a new ridge or trench. The unknown is not empty, it is waiting, and it ensures that curiosity will never run dry. The challenge is balancing imagination with evidence. Science demands proof, and proof in the ocean is hard won. Yet the very difficulty of finding proof ensures that mystery lingers. Perhaps that is why the deep captivates us so strongly. It is one of the few places left on Earth where myths and science still overlap, where discovery is still possible not just in theory but in practice. In that overlap lies wonder. What we can say for certain is that the deep still holds surprises. We know this because every expedition brings them. Strange fish with glowing organs, shrimp with unique vision, microbes with unusual metabolisms, giant siphonophores stretching longer than whales. Each discovery is both an answer and a question. Each shows us how much more there is to learn. The possibility of the unknown is not just speculation. It is evidence repeating itself with every dive. As we think about what might remain undiscovered, we also confront the limits of what we may ever know. The ocean is vast enough that some mysteries may endure forever. Giants may exist that never cross our paths. Microbes may thrive that we never identify. The abyss may keep parts of its story hidden, not out of malice but out of scale. Perhaps that is fitting. Perhaps part of the ocean's power is that it resists complete comprehension. It keeps imagination alive, reminding us that not everything is ours to catalogue. Yet even if the ocean keeps its secrets, the pursuit is still worthwhile. Each discovery reshapes biology, ecology, and our understanding of Earth. Each unknown keeps curiosity alive, ensuring that exploration continues. The possibility of the unknown is not a frustration but a gift. It means the deep will never become mundane. It will always remain a frontier. And while we wonder about undiscovered giants or hidden lineages, another question emerges. Even if we never find them, will the deep always remain mysterious? As technology advances, as mapping improves, as exploration expands, will the unknown shrink? Or will the scale of the ocean ensure that mystery endures? That question leads naturally to the closing thought of our journey. Does the deep sea keep its mysteries forever, or will human curiosity eventually shine light on even its darkest corners? The question of undiscovered giants and unseen forms naturally leads to something larger. Will the deep sea always keep its mysteries, or will human technology eventually strip away the unknown until every ridge is mapped, every trench explored, every creature catalogued? It is a question not only about science, but about the nature of mystery itself. Some believe that with time and progress, no frontier can remain hidden. Others believe that the scale and complexity of the deep are so vast that it will never be fully revealed. The answer may lie somewhere in between, and the journey toward it is as fascinating as the answer itself. Technology has already transformed what once seemed unreachable. A century ago, no one had seen the Titanic, no one had filmed a giant squid in its own habitat, and no one knew that hydrothermal vents existed. Sonar was primitive, submersibles were rare, and genetic sequencing was unimaginable. Today, multi-beam sonar maps wide areas of the seafloor, remotely operated vehicles film hours of footage, autonomous underwater vehicles run surveys for days at a time, and DNA can be extracted from seawater to reveal species present without ever catching them. These tools have expanded our knowledge immensely, proving that progress is steady even if slow. It suggests that many mysteries will eventually yield, not because the ocean allows it, but because persistence does. And yet every advance reveals how much remains. Each time a new area is mapped, it shows features we never suspected. Each dive uncovers species never catalogued. Each experiment suggests new processes we had not considered. Far from shrinking, the unknown often expands with each discovery, because each answer raises more questions. Hydrothermal vents did not solve the puzzle of life in the deep, they multiplied it. Genetic sequencing did not close the book on biodiversity. It opened a new one, filled with unfamiliar codes. The deeper we look, the larger the frontier seems to become. This paradox suggests that the deep may never be fully known, not because it is impossible, but because it is inexhaustible. Mystery is not only about what we have not seen, but about what we cannot yet explain. Even if we catalogue every species, their interactions, adaptations and histories would take centuries to understand. Even if we map every trench, the processes that shape them would keep shifting. The ocean is dynamic, not static. Knowing it once does not mean knowing it forever. Its mysteries regenerate, just as ecosystems regenerate, always giving us more to ask. There are also practical limits. The cost of exploration remains high. Funding remains modest. Human priorities shift with politics, economics and culture. It is unlikely that the deep will ever receive the same level of attention as space or surface ecosystems. That means progress will always be partial, leaving large areas unmapped, large species unstudied, and large processes only roughly understood. Unless priorities change dramatically, the ocean will keep many of its secrets simply because we will never commit the resources to unlock them all. But perhaps that is not a failure. Perhaps mystery has its own value. The unknown inspires imagination, fuels curiosity, and keeps exploration alive. If the deep were fully mapped, fully explained, Would it hold the same fascination? Part of its power lies in what it withholds. Myths of monsters, questions of origin, and visions of unseen worlds all thrive because the ocean resists complete comprehension. Its mysteries remind us that Earth is not entirely tamed, not entirely known, and not entirely ours. In an age when satellites and data seem to reveal everything, the deep stands as proof that mystery endures. The ocean also teaches us humility. For all our technology, we are still fragile creatures on the surface, dependent on machines to glimpse even a fraction of what lies below. The abyss reminds us that human knowledge is partial, always expanding but never complete. To accept that is not defeat, it is wisdom. It acknowledges that discovery is a process, not an endpoint, and that some mysteries will outlast us, just as they have outlasted generations before. Still, it is worth considering how much progress is possible. With advances in robotics, artificial intelligence, and materials, future explorers may build machines capable of reaching trenches repeatedly, mapping them in detail, and monitoring them over years. Networks of sensors may record currents, chemistry, and life in real time. Genetic monitoring may catalogue species without ever capturing them. Satellites may coordinate fleets of autonomous vehicles that cover oceans systematically. In time, the unknown may shrink dramatically, even if it never vanishes entirely. Whether that future comes depends on choices. If humanity invests in understanding the deep as seriously as it invests in exploring space, the results could be transformative. If not, progress will remain slow, and mysteries will endure longer. Either way, the deep is patient. It has existed for billions of years and will exist for billions more. Its pace is not ours. Its secrets do not depend on our urgency. They will remain until we choose to uncover them, and even then they will not all yield. For now, the balance is clear. We know enough to understand that the deep is vital to climate, to biodiversity, and to history. We know enough to recognize that it is filled with wonders we have not yet seen, but we do not know enough to predict its future, to safeguard its ecosystems fully, or to claim mastery over its processes. That gap between knowledge and need ensures that mystery will remain, whether we like it or not. And perhaps that is as it should be. Mystery is not an obstacle to science. It is its fuel. Without unanswered questions, curiosity fades. Without curiosity, exploration ends. The deep keeps its mysteries not to taunt us, but to remind us that knowledge is never complete, that the world is larger than our measurements, and that discovery is always possible. That reminder is not only about the ocean, it is about life itself. So, will the deep sea keep its mysteries forever? In some ways, no. Technology will continue to advance, discoveries will continue to accumulate, and many questions will find answers. In other ways, yes. The scale, complexity, and dynamism of the ocean ensure that mystery will always remain. Even if we mapped every ridge, new vents would open. Even if we catalogued every species, evolution would create new ones. Even if we understood today's currents, tomorrow's climate would reshape them. Mystery is not static, it regenerates, just as life regenerates. Perhaps the better question is not whether the deep will keep its mysteries, but whether we will keep our curiosity. The ocean will remain vast whether we look or not. Its secrets will endure whether we seek them or not. What matters is whether we continue to wonder, to explore, to ask. Because as long as we do, the deep will never be silent. It will always answer, not with everything, but with enough to remind us that Earth is still a frontier. And so, as we reach the end of this journey, remember that the deep sea is not simply water and pressure. It is memory, history, ecosystem, and mystery. It is the unseen world beneath our feet, shaping our climate, recording our past, and hiding our future. It is not a place apart. It is part of us. To explore it is to explore ourselves. To leave it unknown is to leave ourselves incomplete. Whether its mysteries last forever or not, they will always call to us, pulling at imagination, reminding us that discovery is never finished and that wonder never ends.